Hello, welcome to XDC 2020 with a little hiccup at the beginning. Now we are ready to start the opening session. Sorry for this short amount of time we've been late. We've had some technical difficulties. We hope not to show up again. This is our first virtual conference. We are really excited. I hope you are excited as well and can't wait for the talks to start. So I will not take more than 10 minutes of your time, and we'll jump through some of the useful information about the conference talks and how to interact with each other and with the organizers as well. I think first we should start with saying a big thank you to all our sponsors and organizers. So off we go. Thanks a lot for organizers, for Intel and X.Org Foundation for pulling this off. Without you folks, it wouldn't be possible. Thank you for sponsoring the conference on platinum level. What goes to Intel Corporation. Google sponsored gold level this year. Thank you, Google. We have another gold sponsor, it's NVIDIA. Thanks a lot for sponsoring XDC. We have many great silver, bronze, and supporter sponsors. Thank you, Collabora, Igalia, the Linux Foundation, Microsoft, AMD, ARM for sponsoring on silver level. Thank you, Kronos Group. Thank you, Dorota. Thank you, GitLab, for sponsoring on bronze level. We would like also to thank, say big thank you to all our supporters on Code Weavers and also by donation for website done by LWNet. Great, we've finished the first big section. We have a couple minutes left, so let's jump into the useful information for everyone. So XDC is meant to be very interactive conference from experts for experts. So we will be trying to bring some of the experience that everyone had on previous XDC that were handled like physically. Now we are in the situation where the conference is virtual. We are doing our best to bring some of those experiences you had in the past to actual virtual environment. For this matter, we have prepared attendees how-to for everyone attendee. There are details on how to interact with each other, how to use our online Jitsi instances to create some for you to interact and bring some more ideas, work on stuff that you think is interesting. We also have IRC channels that will provide you opportunity to ask questions to presenters, as the main streaming is going live on YouTube. And also there are capabilities for people that are particularly interested in the topics to join the Jitsi rooms live and ask questions or interact with the speaker. Everything is described in the attendees how-to that was sent out to every registered attendee. So please take some time to review it once again. And in case of any questions, reach out to us on IRC on Freenode. We have Twitter account. We are posting all updates on a regular basis. Make sure that you follow us on Twitter so you get all the news as quickly as possible from the team. Jumping to the program. So I didn't put the program to the slide deck this year because probably it would be strange to read those various time zones as we are spread all over the world. So I strongly suggest you go and review the program that is available on XDC webpage. And we have some tip for you. By default, the time zones are set to UTC, I believe, but you can easily change it to fit your time zone, just going to preferences and setting it to your time zone. It should display all the talks aligned with your time zone. So it will be easier to pick and choose which ones you are able to attend. For lightning talks and demos this year, as we are virtual, there is not that much flexibility for moving those around between the days. So we of course will allow new lightning talks and demos to be added to the schedule. Currently, today's schedule, where we have one demo and multiple lightning talks, is full. We have time left on Friday, so if there is any topic, any demo you would like to share with the attendees, please make sure you contact the organizing team, and we will make sure you have the ability to do so. There will be one rule though. Lightning talks will take precedence over demos on Friday. So first come, first served basis here. Rules for those talks are the same as previous years. So 5 minutes talk for lightning talks and 10 minutes is allowed for a demo. Again, just a reminder, all the questions you have, we have IRC channel on Freenode, XDC 2020. Feel free to reach out and ask questions there throughout the entire conference. We have one workshop lined up. It's happening tomorrow. And in the schedule, if you go to the website, the workshops will be marked in nice orange color. So feel free also to take a look at what we have in plans. And if you would like to add one another workshop, there is still room for that. Please contact organizers again, as in previous cases, and we'll help accommodating that. As every year, it is good to remind that X.Org Foundation and organizers as well, we are dedicated to providing you harassment-free experience. So we do not tolerate any harassment from any participant or speakers or organizers as well in any form. So make sure that you review the code of conduct. All speakers have signed up for this code of conduct as well, and we have very nice experience without any code of conduct violations. In case of any breaches to the code of conduct, please contact me on IRC. I'm Radek from the organizing team. There will be my email. My email is all over the place on the website. Also, I'll be available on IRC. In case of any breaches are happening, make sure it's immediately made visible for me so we can take actions. I hope that I didn't take too much time and we can jump right away to next to the agenda of our conference. I'm really happy we managed to bring it to you virtually this year. I hope you'll have great experience. Please be understanding in case we are meeting any technical issues. This is first time for us, and I'm super happy to have. Sorry, double voices. I'm super happy for being able to bring this conferencing experience back to you. So see you around. Have really good conference, and I hope everyone will learn a lot of new things and will find new people to interact with. So that's all I have. Thank you very much, and talk to you. And see you around, if I can phrase it this way. Thank you.
Thank you, Radek. I just want to say that, so Martin Perez here. I'm physically hosting the conference from my basement, along with Arek. So Arek, Radek sounds similar, but they are two different people. And right now we have about 170 viewers. Pretty nice. Okay, so in about a minute and 30 seconds, we're gonna have Iago speaking. I'll move to this and see you there.
So this is overview of the open source Vulkan driver for Raspberry Pi 4 by Iago Toral. Iago, the stage is yours.
Okay, thank you. Hello, my name is Iago Toral. I work as a software engineer for Igalia, and for a bit over a year now, I've been involved with the Raspberry Pi graphics stack, and initially with the OpenGL stack, which was the only one available. But more recently, I've been working on bringing up Vulkan for the Raspberry Pi 4, and that is what this presentation is going to cover. So I hope you enjoy that. This is a list of contents that I prepared for this presentation. I would like to start with a quick recap or a quick insight into the development story behind this driver, mostly giving you a view of the main milestones we went through during development, as well as some of the things that we, some of the ways in which we approach the development from the start of the process. Then we would like to discuss a little bit about the current state of the driver, what's currently implemented, what is working, what we have tested so far, and what you can expect from it. Then I would like to also discuss some of the implementation challenges that we went through. As you know, Vulkan being a multi-platform API, there is always certain aspects that you need to consider more carefully when you implement it in a particular platform. So I would like to give some insights into what we had to do specifically for V3D. I think that might be of interest for some of the more, for the people who are more involved with GPU drivers out there. And then I would like to, of course, cover the future plans that we may have for the driver, both in the short term, as of in this year, as well as in future years, if possible. And last, I would like to make a note on how we can enable developers to contribute. I know that when the Raspberry Pi Vulkan effort was announced, there was a lot of excitement around it, and there were a few people who were interested in helping us bringing Vulkan to Raspberry Pi 4. So I think when we started this effort, the scenario for allowing other people to contribute to the driver was not optimal. And there were a lot of challenges involved with that, which I'll discuss a bit later. But I think we are now in a much better position to enable other people to have a great experience contributing to this driver. And I would also like to talk a little bit about how we can do that. Okay, so let's get started then, talking a little bit about the development story for this driver. So first, the code name for the driver is V3DB. So obviously not a very original name if you are familiar with previous drivers for Raspberry Pi boards. This is basically taking the OpenGL driver name and just adding the V for Vulkan at the end. Hopefully that will make it easy to identify for Raspberry Pi users. We did discuss some more original maybe or different names for the driver in the beginning, but eventually we thought this was the best option. So this is being developed as a Mesa driver. Development is not happening in the upstream Mesa repository, but in a fork. We did this for our own convenience mostly. When you are bringing up a new driver from scratch, there is a lot of moving pieces throughout most of the development. A lot of things that we then would like to come back to and amend in the commit history and things like that, which is obviously not the right workflow for working directly within Mesa upstream. So I think this was useful to us, and when it's the right time to merge the driver or to propose to merge the driver upstream, I think we would be able to propose something that makes more sense from the point of view of the history of the development. We are actually at the point now where I think we are close to do that, and I will discuss a little bit more about that later in the presentation. So as a Mesa driver, our work leverages some other parts of infrastructure in Mesa, and notably the Vulkan Windows System Integration bits that were developed originally for Anvil and then abstracted away so that it could be reused with RADB. We, of course, use that. We also continue reusing the V3D backend compiler from the OpenGL driver, which is based on NIR. We just expanded it as it was necessary to cover some of the Vulkan specific features and semantics. Of course, in this process, we also reuse the SPIR-V translator layer to near. And this is something that may or may not continue to happen in the future, but at this point, we are also using the same kernel interface that we use with the OpenGL driver. Initially, this was decided to make things easy for us, as we would be able to just focus on the user space side of the driver. But it has been working really well. Of course, this may impose some limitations for us that we may want to assess a little bit more in detail in the future to see if we can, if there is gains for us in possibly having a dedicated interface for Vulkan, or maybe extend the existing OpenGL one for Vulkan. We still need to assess what would be the advantage for that and how much gains we can get for that. But for now, at least, we are using the same kernel interface, and that has made things a lot easier for us in some ways. So this slide presents a bit of a timeline of the development. We started developing the driver sometime by the end of November, I believe. I think it was not until the beginning of December that we started like fully working full time on it. So the developers are Alejandro Peñeiro and myself. We have been working full time pretty much since that moment on this project. If you have been following the news around the Raspberry Pi, you probably know that the Raspberry Pi Foundation announced this Vulkan driver effort by the beginning of February. And that was after we achieved the first milestone for the project that we had, and that was getting this triangle demo that we used in that post, where we basically got that first vertical slice of the driver working and rendering something on the actual hardware. Since January to May, it has been basically a few months of just working on iteratively adding more and more features to the driver, to a point where we thought we had something that started to be useful. It was at that point that we wanted to move development to an open repository and give users a taste of what we had developed so far. And in order to do that, we wanted to give them something that they could, test on their Raspberry Pi 4s. And it just happened that Sasha Willems has this great repository of demos for Vulkan, which are very popular in the Vulkan ecosystem. And it was then, I think that was the first time that we actually tried to run any actual Vulkan code that was not just a small CTS test or some small sample that we developed ourselves to aid during development. And it was really nice to see that there were many demos that were already working. So we used that to go ahead with moving to an open repository and give people access to the driver code and point them to this demo so that they could just play a little bit with the driver. I think that was very, very nice. Then when we made that move, we also kind of shared a few notes on what we were planning to do in the upcoming months. And one of the points I made then was that I did not want to work on enabling any games yet. And the reason for that was we wanted to focus on getting a conformant Vulkan 1.0 implementation, both conformant and complete, of course. And because, if you start trying to figure out why a game doesn't work or doesn't render correctly too early, you are just going to have a very hard time. It's a lot easier to just fix most bugs as you can just by fixing more self-contained CTS tests. I thought that was the right thing to do, and I still think. However, just as I made that plan, a colleague of mine asked me whether we were able to run Quake at that point, and we were not able because we didn't support complete shaders at that moment. But we checked Quake 2, and it just happened that it was using a subset of the Vulkan API that we were implemented. So it was too tempting not to give it a try. And when I did, I found that it was not working. It didn't even start. It just hung the GPU, which was very frustrating, to be honest. So I decided it was maybe worth my while to spend a few weeks trying to get it to work, to understand what was going on. Since at the end of the day, it was using features that we were supposed to work. We did that for VKQuake 2, and then in parallel, we were continuing developing features for things, including compute shaders, so that also enabled us to run Quake. And then we also saw that we were able to run Quake 3, but it required a couple of optional features that we also implemented. So long story short, in a span of over 3, maybe 4 weeks, we implemented support for all these games. And then we also, for the first time, I think, during development, we got a real taste for performance. And we found that it wasn't really good at that point, not unexpectedly though, because we knew we were not taking care of some of the basic performance enablement in the driver up to that point. So we used that opportunity to do that, and we got all the games to run very smoothly on the Pi 4. And then from that point onwards, I think we just focused on getting the remaining set of features to work. I think we achieved that by August. By the end of August, I think we finished with multi-sampling and robust buffer access, which I think were the only ones that were missing at that point. And I think at this point we have a minimal Vulkan 1.0 implementation running, and we are focusing on getting better pass rate on CTS. Okay, so as I said before, our first milestone was to get something to run on hardware. For us, this was very important. We didn't want to start building a lot of infrastructure for the driver and then have problems to actually get basic things working. So as you know, when you're bringing up a new driver from scratch, there is a lot of pieces that need to work together correctly for you to be able to put pixels on the screen. We wanted to prioritize getting that done right, so that kind of vertical slice of the driver working. And then once we got that in January, we moved on to just a more iterative feature development, where we would just choose something that was not implemented yet, and we would implement that in the driver. And the idea with this was to use the Vulkan conformance test suite that Kronos developed to guide our development efforts. So basically, this, for those of you who don't know, this is a huge test suite that has hundreds of thousands of tests for testing everything that has to do with Vulkan. And this is used for conformance, but also it's very useful for developing drivers, right? As it gives you the sample test that you need to check your own feature development as you bring them into your driver. So of course there is some time between the moment in which you get that first triangle and the moment in which you are ready to start running CTS tests, because the CTS assumes that you have a full driver at the end of the day, and every test assumes that certain functionality is there. And so you have to make sure that you have at least these fundamental pieces of functionality in your driver to start enabling CTS coverage. But once you get there, you can just start using CTS to test everything that you do. And that was very, very useful to us. The other nice thing about this process is that at the same time, we had other people at Igalia who was working on improving the CTS coverage. And we were in an excellent position as we were developing this new driver to identify things where the CTS coverage was not great, particularly for our platform. So we had this nice ongoing discussion with this other team at Igalia, where we could just tell them, okay, for this particular feature that we have implemented, we are seeing the CTS coverage might be missing something here. And this ended up improving the CTS coverage over time, as our colleagues would then go and implement new tests for this, which I think was really nice. So another thing that we did during development, we were very worried about regression testing. But here we wanted to sort of try to strike a good balance between having good coverage to prevent any regressions, but at the same time having something that didn't take too long to execute, because we did want to be able to run these very frequently, even multiple times a day, as we made progress with development. So we use Parallel DQP Runner for this because it allows us to run multiple tests in parallel, as you probably know. And the other thing that we did is that as we were growing our feature set, we would select a subset of the CTS tests that we were passing with each new feature development that we added to the driver, and just select a subset that we thought was meaningful to check for regressions, but at the same time that it wasn't too large to have a huge execution penalty. And to give you a sense for what we settled with, right now we are passing about a bit over 100,000 tests of the CTS, and we're using about 10% of that for this subset that we use for regression testing. And this has been working really great for us. We can run these tests very quickly every day, and we have got like maybe 95% of our regressions during development with this system. Of course, as our driver progressed and got more mature, we were also able to start running the full CTS. The running times got shorter, and also they were stable enough, because when you have a half-developed driver, you can easily run into all sorts of troubles, including GPU hangs, so you don't want that, right? But as we mature, we started to do this as well and catch any regressions that were not caught previously by this subset regression testing that we had. But as I said, this was rarely the case that we ran into problems. Another thing that we did that I think was useful was this kind of assert everywhere philosophy that we had. So this was not just for preconditions on the Vulkan API states explicitly, but also for things that we assumed during development, things that we knew were not completely implemented, paths that were not existent, whatnot, like everything we would assert there, with the idea that at any point, any test, anything that we tested that would hit something that we knew in advance was not fully there, would assert and crash early, rather than maybe continue through it and lead to a GPU hang or some other obscure incorrect rendering or failing test that would be much more difficult to then track down to the real problem. We got a lot of things with this. Even for CTS, when we were running CTS, we would find that we were running CTS tests to test a specific feature, and some of them maybe would crash early because they were using a feature we were not aware of they needed. And it's very nice to just see a crash immediately telling you that the crash is because of that, and you don't have to go in and see what the hell is going on. And the other thing that we did, especially during the last few months of the development, was to try to keep people updated on the progress through developer blog posts. I guess some of you may have seen us doing that. I think it's a nice way to keep people informed about progress. All right, so moving on and to describing the current state of the driver. So as I already said, we think that we are now at the point where we have a minimal Vulkan 1.0 implementation. Vulkan comes with a lot of optional features. We do implement a bunch of these, but we have tried not to go overboard. So there are a lot of optional features that I think we want to implement that are not there just yet. Then there is, of course, a lot of extensions on top of Vulkan 1.0 that we have not implemented that we probably should. But at least we have this Vulkan 1.0 minimal feature set there, I believe. Our focus right now, as I said, is getting all those CTS tests to pass. Right now, we are passing around 110,000 tests, and we only have 20 test fails right now. So we are actually pretty close to be conformant. So I hope we can start moving things for that real soon. We haven't done much real-world testing with the driver yet. We have been mostly testing through the driver with CTS tests and some samples that we write now and then. The only real testing we did was with the Quake games, as I mentioned before. We know that all the 3 classic games for Quake are running. We also know that some people have been playing Open Arena, which is based on the Quake 3 engine. And we got news back in July, I think, from Salva from the Raspberry Pi Labs, who has this channel where he does extensive testing of a lot of games on the Pi and also the boards. And he tested our Vulkan driver with some PSP Vulkan emulator, and he reported that he had some games working already there, which was it's very encouraging when you are in the middle of developing something and your head's down working on features, to have someone telling you, hey, I'm testing this and this is already working. That was really nice to hear. As we also announced through our developer blog posts, we also got a lot of demos from Cecil Williams working. We have been updating through this developer blog post on this. It's another nice way to visualize your development progress, other than just a increase in CTS pass count, right? Regarding performance, we haven't done much yet, as I said. Mostly the only performance work that we did was to get the Quake games running smoothly. We can say, though, that VK Quake 3 in particular has both a Vulkan and a GL renderer, and the Vulkan render is much faster, which is very encouraging. Of course, the GL rendering is based on GL1, so it's not the most modern implementation, I guess, but still, I think it's a good result. For those of you who know Quake 3, you know there is also a GL2 renderer, but that's more of an experimental thing that adds a pile of other rendering features, so the performance actually works with that rendering, even if it's more modern. So that's why I think the comparison with the GL1 render is the best. So another thing we are aware of currently is there are some slow paths in the driver. We noticed this particularly for some cases of transfer operations in Vulkan. In fact, this was one of the things we worked on to improve the various Quake games when we work on that. But I think there is still ways for us to keep improving this. I think we should be doing more of that going forward. Another thing is the hardware has this TFU unit, which is used to basically convert and copy images around, which we think we could probably use better in some areas. Unfortunately, Vulkan allows developers to do suballocation, which of course is a very nice technique for developers, but it's just something that doesn't work very well with our TFU unit, because it allows, basically suballocation means that you can create an image and then you can suballocate parts of that image to smaller images. So you have this mega texture and you then use the memory for that mega texture to hold multiple smaller images as a way to kind of do your own memory management. And then you allow these smaller individual images to be copied, removed, added in different places within that mega texture. And that's something that doesn't really work very well with our TFU unit, because it only works with full images, basically. But still, I think there's room for us to make better use of that in some cases. Okay, so now moving on to implementation challenges. So these are kind of a collection of a few things that we had to be a bit more careful with when bringing Vulkan to B3D. So one of them is, of course, Vulkan expects that everything that you do is going to execute in the GPU. The idea is that you have this command buffer in which you record all your rendering commands. Then you submit that to a GPU queue. And then when that's done, the GPU will signal your host CPU using fans, for example. And all this works really well for us as well, of course, but there are very few selected cases where there were specific things that we needed to do in the CPU because our GPU just didn't work like that. Off the top of my head, I remember the case, for example, for occlusion queries. So when you want to get the result from an occlusion query, the Vulkan API allows you to just record a command into the command buffer, where the GPU just writes the result of the query into a buffer that you can then access from the host of the GPU. And in our case, it just doesn't work like that. So the only way I think that we have to read the result of an occlusion query right now is to just map the buffer, read the result, and then copy it in the CPU. This is in fact what the OpenGL driver does. So what this means is that for us, we need to kind of break the illusion internally that everything is executed in the GPU and have these internal flashes in these cases to synchronize between the CPU and the GPU, do the CPU part of the work, and then resume the execution of the common buffer in the GPU, which caused some implementation churn, of course. But it's, I think, unavoidable, at least in some of the cases that we had this problem. Maybe in the future, some of these bits we could improve. I had some ideas for how to maybe make reduce this churn in a few cases, but I think it's maybe not possible to do this in exactly every single scenario. But as I said, this is just only a very few selected scenarios, and I don't think it's a major cause of concern for us. Another thing that we have in the Raspberry Pi 4 is a display pipeline that can only handle linear images, whereas our render pipeline cannot sample or texture from linear images at all. So, funnily enough, the Windows system bits in Mesa for Vulkan assume that any of your swap chain images are going to be images that you can texture from by default. But that's not true in our case because of this. So we have to disable that feature on the Pi 4 for now. Of course, when you are running inside a compositor and inside a window and you're not full screen, you may be able to negotiate a tile layout for your swap chain images. But I wonder whether that's worth it or not, in the sense that that basically means that when you switch between full screen and window mode, the underlying capacities and capabilities of your surface are changing as well. I'm not sure if developers, that's in a scenario that developers expect, or even if it is worth it, because it would also mean that it would require to do to have an alternative implementation if they need to switch back and forth between these two modes. So another thing that is very core to the Vulkan API design is this idea that you have all your pipeline staying available upfront, so to avoid pipeline shader recompiles at runtime. And this is a kind of one of the great ways in which Vulkan can improve the user experience. And this works really well as well for us. However, there is this one or two cases where we cannot exactly do this, or not optimally, because we don't have all the state that we need. Particularly in our platform, we would like to know when a shader uses textures, we would like to know the formats of these textures. And this is something that we don't know until we bind descriptor sets later on, not when the pipeline is created. So the way we are dealing with that right now is we decide to precompile a few variants with the pipeline. So we have an optimal case that assumes that we can use a 16-bit return size for all the textures that we have, but we also compile a fallback case where we use 32-bit, which is maybe not as optimal, but it is going to be valid in all cases. So then when we actually bind descriptor sets, we choose the one to use based on the formats that are actually bound at the time. Of course, we could go further into this strategy and produce all the combinations maybe, and always choose the optimal case, but then we would be creating a lot of shader variants that we maybe not be using at all, and they would use memory. So we sort of settled with this for now, but this is an example of something that we may want to tweak a little bit going into the future as we start playing around with more applications and evaluate how we can optimize these kind of things. For what it's worth, with the Vulkan Quake games that we tested, this didn't seem to have any significant performance impact. Maybe we would drop half a frame per second or maybe one, but not more than that. So we don't think this is a huge thing, but it's something that we would like to point out. So yeah, the other thing is, so Mesa has a Vulkan Windows system implementation that we can reuse in different drivers. There are two paths implemented there. One that is optimal, where your swap chain images are sent directly for scan out, and the other one which acts as a fallback, where the images are converted to a linear buffer, and then it is the linear buffer that is sent for scan out. So the optimal implementation path requires that you have a PCI GPU and the PCI bus info extension implemented in your Vulkan driver. So the Raspberry Pi display device is not PCI, of course, and I think what we need there is just to make sure that the DRI3 device matches the drivers, and in that case, we should be able to avoid the slower fallback path. So we have actually a request for comments, merge request on the upstream Mesa repository to kind of gather thoughts on this issue. We proposed something there that works for us. I recently updated that solution. I would like to get a bit more feedback on whether that's the way to go for this. Okay, so moving on to future plans. So in the very short term, there is a couple of things that are very important. Of course, we are very close to conformance for Vulkan 1.0. I mentioned before that we are only maybe 20 tests away from achieving that. So that's something that we are working on and that we would like to see happening this year. We also, the other thing that is very important to us is to move the driver to Mesa and merge it there. As I said, for our own convenience, we have been working outside of the main tree just because we could not offer a good, I think, developer workflow as we wanted to, go back in history and amend things that we had done there in the past. But I think the development context for the driver nowadays is much different. I think we are much more stable. I don't think we need to do that anymore or be concerned with that anymore. And I think working upstream directly nowadays makes a lot more sense. I think the driver is also started now to be useful. It can run a few games. It can run a few demos. I think that's what people would expect from a driver in Mesa. So I think we are in the right place to start that conversation. We have been discussing this internally this week already, and we have some thoughts on how we can propose to do this that we hope to share even this week with the main Mesa community through an email on Mesa Devel. So look forward to that. So in the long term, there is a lot more that we would be willing to explore with no particular order and priority. One of the things that I already suggested is better TFU unit usage. I think that might improve performance in specific scenarios, at least when we are not sub-allocating resources. So I think there is maybe a few ways in which we can take advantage of that. And we are already using the TFU unit in some cases, but not maybe as thoroughly as we should. Another thing we would definitely want to work on is improving Windows system integration. For right now, we are focusing only on the X server, on X11, basically, because that's the Windows system used with the Raspbian OS. But going forward, we would of course also want to support Wayland and even just display because that's something that other people have been asking us for. So we definitely should get to do that at some point. Another thing is, if you are familiar with Vulkan, you know that there is this design element of the API where you have render passes and input attachments. And this was specifically designed to help tile GPUs, like the ones that you usually find in the embedded space, improve their performance in certain scenarios. And we are not yet, our implementation does not yet have an optimal implementation of this. We are just taking input attachments to be regular texture inputs to a subpass, which doesn't take advantage of the mechanism that Vulkan enables for embedded GPUs to have a better use of the data that is already on your tile buffer. And I hope that we can get to do that at some point in the future, that optimization. We actually noticed that there is a game, VK Quake 2, that users do this functionality of input attachments. So it would be nice to implement this and see how it affects our performance. Then, of course, there is a lot of optional features and extensions on top of Vulkan 1.0 that we could implement, that we would like to implement for sure. And as we make progress with that, we should also assess if we can do Vulkan 1.1 or how much of it we can do. Vulkan 1.1 is something that we haven't really think about yet, but we should definitely have to do that at some point in the future. Another thing that we'd like to improve going forward is code reuse with the class driver. So the philosophy that we followed during development is that we did not want to, when we found parts of the class driver code that we could reuse in Vulkan, we did not opt for refactoring the class driver at that point, because the Vulkan driver was in a very early development stage, and so I don't think we had a good visibility on exactly how that code that we were refactoring would need to change for Vulkan. And we didn't want to start creating mesh requests for the class driver in Mesa and then continually have to be patching that as we made progress with Vulkan. And we also didn't want to keep the changes local to our fork, because then as progress was made on upstream Mesa on the class driver, then we would have to deal with that on our end and complicate rebases. So we just took the code that we needed into Vulkan, made whatever changes we needed to make to adapt to whatever we needed to do in Vulkan. And I think now that we have a more mature driver, we're in a better position to assess how we can effectively reuse code and refactor that code to be useful across both drivers. And I think that's a nice little project that we can run, hopefully soon after we land the driver in Mesa. And then there is, of course, a lot of other features that we implemented in Vulkan that could be ported to class. For example, one thing that I remember Eric had told us was the class driver is not using efficiently the hardware for multi-sample resolves. It's using a shader instead, but the Pi4 allows us to do that. So this is something that we did right for Vulkan, and it should be straightforward to port it to class. So we should do that. And then there is a few other features like sample rate shading or robust buffer access that we implemented for Vulkan that should be easy to enable or port to the class stack. So we should definitely look into doing that as well. But I think that the most important thing for us right now is to get to test the driver with more real world applications and games, to get a real feeling for what is really working well, what doesn't work, what is underperforming, and use all that feedback to continue to improve the driver, polishing the bits, fix the implementation, and polishing the bits that we need to polish to improve performance. Okay, so now let's talk a little bit about how we can enable other people to contribute. So as I said in the beginning of this presentation, I think in the beginning of when we announced the effort to bring Vulkan to the Raspberry Pi 4, we're kind of taking our first steps with the driver. The development there was, or the context was not very friendly to other contributors. I mean, there were a lot of moving pieces. Even internally, we have to be very careful about how we wanted to coordinate so that we didn't step on each other's feet. I think now that when we arrived to May, I said that we had a lot more implemented, and we started to have some of the Cecil Williams demos working. I think at that point, when we decided to move to an open repository for development, I think we started to change that scenario. And I think today we are in a much better context to enable a satisfactory experience for other people to help us with the driver. Now, some people may be thinking that because we are close to a Vulkan 1.0 implementation that there isn't so much that needs to be done, but that's far from true. I just mentioned a few slides ago some of the things that we still want to work on, and there's a lot of there, as you could see. And there's more as I will discuss right in a moment. But first, I would like to address the fact that As you probably know, the Raspberry Pi 4 GPU doesn't have available documentation as of today, unlike the scenario for the Raspberry Pi 3. Some people may think that this is a blocker for them to contribute, but I think that's not the case. Thankfully, we do have a Glass 3.1 open source driver available. I think that this gives you a lot of information about how the GPU works. In fact, I found myself going back to the Glass driver code for reference when I needed something for Vulkan. Then I would go to the technical documentation that we do have available for the GPU, because it is a lot more convenient and it gives you actually a bit more information when you really look into it. So even if it looks a bit more scary than just having a technical documentation, I think people should really appreciate the value that we have in having an open source driver available to help them understand how things work. And then as for how they can get involved, other than some of the things that I already mentioned before, when we were developing, we were adding a lot of fixes to the source code for a lot of different things, from things that we could do better, things where we could maybe improve performance, things where we could not do better just yet because we would need some other feature that we have not implemented today, but that we may implement in the future, and then it would unblock maybe some other optimizations, things where we are not sure we are maybe making the best decision just yet. So there's a lot of things there, and anyone can just read the source code and try to see if there is something for them. Of course, some of these may be trickier than others. Maybe the full story for them is not so immediately obvious to everyone. So if someone comes across any of these and they want to work on something, I suggest that they just talk to us and we can give them all the background required for that, probably. So that at least they understand the effort that's required with these things. And then, of course, there are many optional features, as I commented before, that are pending and people could work on them. And one of the things that we would definitely welcome would be testing and performance feedback. So just getting the driver, testing some Vulkan games and Vulkan applications, and letting us know what works, what doesn't, if the performance is decent or not, and then we can use all that feedback to try to figure out how to improve the driver. That will be tremendous help to us as well. So if you are interested in doing any of this, or you just want to ask questions about the driver or anything, here are a few resources. We are hanging out on the video core channel Freenode. So just join the channel, talk to us, ask questions. We will be happy to hear from you. Then we are, of course, on Mesa Devil as well. So you can reach out to us there as well. And we can also interact through GitLab issues. Right now on our own fork where we are developing the driver, but hopefully not very far from now in upstream Mesa directly. Now I have one last slide where I would like to share special thanks to many developers who have directly or indirectly helped us in this process. First, the Mesa community for developing not just developing, but continuously improving, optimizing it, and adapting it for Vulkan. Obviously, all that work has been super useful to us, and we were able to just reuse a lot of it directly in our driver, making our lives a lot easier. The Spearbit translator layer, of course, that's also related to this. The Windows system integration bits that I mentioned before in my presentation, all these things made our lives a lot easier, and the development effort smaller than it would have otherwise been. Even when you may think that Vulkan is a low-level implementation and there is less room for sharing code than in GL, but that is true. I think there is still relevant stuff that we can reuse in Mesa. I'm very grateful that all the developers did all this work before, so we can leverage that in our driver. Then, even if we have multiple Vulkan drivers in Mesa already, and each one has its own target platform with its own quirks and its own requirements, I think they were still, despite that they were different platforms, very inspirational and useful to us. Anvil, Radbee, and Turnip, we would usually go to these drivers to have a look at how they solve specific problems, how they implemented specific things, and if they had to attend to the same concerns or issues that we have on our platforms. And just having that code available is just great help in general. So I would like to thank everyone involved with the development of these drivers explicitly. And then there are two other people who I would like to thank especially, and these are Eric, who was the original developer of the Glass driver code. And obviously, as you can imagine, having a 3.1 Glass implementation available just makes developing a Vulkan driver for that same GPU a lot easier. So Eric solved a lot of the problems that we would have to solve for Vulkan. He solved them for OpenGL. So we could just take advantage of that. Yeah, I'm just finishing. And the other person I would like to thank is Dave Emmett, an engineer from Broadcom, who is has been super helpful with us for those moments where you hit a bug in the GPU or something that doesn't match the documentation that we had, or that was not working as expected. He has been super helpful with us as well. So big thanks to him as well. And that's all. So I hear that we have some questions. Okay, good.
So the first question from IRC is, have you considered compute shaders for occlusion queries? They do that in RadV to mangle all the query to buffer stuff, and it would avoid a CPU fallback.
Oh, that's very, very interesting. No, actually, I didn't think about that. But yeah, that's one thing that we should try, maybe. Yeah, thank you.
Okay, another question is, have you tried running Zinc on top of this driver?
No, I think someone else, I think Salvador from Raspberry Pi Labs asked us if there were any requirements specific. We haven't tried to do that yet. I guess it would be an interesting experiment. I'm not sure exactly what are the requirements that Zinc has on the Vulkan implementation. Maybe now that we are close to the Woerner implementation, we would be close to that. We don't implement a lot of optional features and extensions, so maybe there is stuff that we are missing that they require. I guess it would be nice to know how that works.
Okay, another question is, how much code can you share between your Vulkan driver and the OpenGL driver, and how did you deal with the difficulties in doing so?
Right. So one of the things that we could share without any problem is the entire compiler backend. So all that is just works the same. We only had to add a few additional features where Vulkan has specific intrinsics that we have to implement that are specific to Vulkan, but the general backend compiler is the same. The other things that we can reuse have to do, for example, with image layouting. So when you create an image and you have to decide where in memory each of the maps go, how big they are, or alignments, and basically the layout of your map chains and layers, all that we should be able to share, for example, and that kind of thing.
Okay, do you have any V3D GitLab CI runner set up to prevent regressions when things let upstream?
Right, so not just yet, but that is in the plans. So our plan there, which is a bit overdue at this point, is to plug. We have an internal CI that we use for the Raspberry Pi 4 Glass driver that we want to plug to FDO. And we have been working. We have a colleague who has been working on that for a few months. Unfortunately, that work is not just yet at the point where we can do that, but we hope to do that soon, I guess. And then once we have that, we would like to expand our CI to also incorporate the Vulkan driver so that we get coverage for all the relevant drivers.
There's a comment, very good work. I'm really excited to see more Vulkan drivers. So there's more of us. Excited about this.
Thank you.
And one new question that just appeared. Any plans putting Any plans on putting here the reduced CTS test list in the CTS repo? So do you want to put that test list in the repo?
Oh, yeah, I guess we could do that. We do have a internal repository with Piglit where we keep a list, but I guess we could put that in the repo as well. Yeah.
Okay, I guess that was the last question. Thank you very much for your talk. It was great, and see you around.
Okay, thank you. Enjoy XDC.
Hi, we're here from Microsoft to talk to you about innovations that we've been working on in the Linux and WSL space. My name is Natalie. I'm a developer on Direct3D at Microsoft.
And I'm Steve Pronovost. I'm the lead for the Windows graphic kernel, also at Microsoft. And we're super excited to talk to you guys about some work we've been doing over the last year on Linux, and especially on the Windows subsystem for Linux. And we have 3 talks this year that we prepared together for XDC. So this talk specifically is about how we're bringing GPU hardware acceleration inside of WSL. So I'll be talking about how it works on like the kernel side of things and the host side of things. And Jesse's going to be talking about the user space. And then we have a second talk where we're going to be talking about like how we're bringing also GUI application to WSL. So the ability for user to run X11 and Wayland application.
And then after that, I will have a talk about work that we've been doing inside the Mesa project for building mapping layers for OpenGL and OpenCL on top of D3D, both for use on Windows and WSL.
We hope you enjoy our talk. So what is WSL? WSL stands for the Windows Subsystem for Linux. And in short, it's an infrastructure in Windows that allows a user to run Linux application. And in particular, Linux console application. So you can think about it at the high level. Windows is hosting a version of Linux, and the user can go and launch application within that environment, and then those application gets integrated back onto your Windows desktop. But today, this is only a console experience. I mean, you can run whatever you want as long as it's a console application. And why WSL? Like, why can't a user already do this by, for example, just creating a virtual machine in Hyper-V and loading Linux inside the virtual machine and running Linux application that way? You can totally do that. But managing the VM is a little bit of a pain, and it's not very user-friendly. With WSL, we're trying to enhance the developer experience to make it easy for a developer that needs to go and use tools that run in a Linux environment or tools that run in a Windows environment to be able to use both of those from the comfort of their PC. So, you know, they may have some tools that work better on Windows, they may have some tool that works better on Linux. And this gives them a way to basically run their entire workflow in the entire environment. And essentially get the best of both worlds without having to deal with like clunky setup of like, you know, dual booting into Windows and then Linux, or having to deal with multiple PC, or having to manually manage a virtual machine. So WSL today looks something like this, where like the screenshot I have like a Windows command prompt, and I also have basically like a bash on Ubuntu, where basically that this is an actual version of Ubuntu. You can log into it, you can go in and launch application, and standard out is essentially like forwarded back to Windows, so it looks like just a regular console onto your PC. So you have this nice terminal integration. But it goes beyond that. So we do things like, for example, file system integration. So your like Windows files are automatically mounted inside of the Linux environment. So it's very easy to go and access your files. And similarly, all of your files in the Linux world are available on the Windows side through like Explorer. We also enable things like Linux and Windows interrupt. So if you have a tool that works better on Linux and you have a tool that works better on Windows, you can have a Windows tool go and call an executable inside of Linux and wait for some result from it. And similarly, a Linux tool can basically go and call into like a Windows tool. So you can have script that basically bridge the two worlds. And there's many more. But the key thing today is that it's a console-only experience. So today we have 2 forms of WSL that you'll hear us refer to, WSL1 and WSL2. WSL1 essentially is we were running just the Linux user space, essentially inside like what we call the Pico process. And you can think about we had a special kernel trap, so that as the process calls into kernel, we would go and trap these, and then we would emulate a Linux kernel on top of like NTOS. And this allowed us to run like Linux application, but as you can imagine, it had some performance issue, it had some compatibility issue, because we could not perfectly emulate like a Linux kernel. With WSL2, we further improved this to now start running inside of a virtual machine instead of running inside of a Pico process. And one of the things that this basically allows us to do is to now run like the full Linux. So we run both user space, but we also now run an actual Linux kernel. So that gives us better performance. It gives us better compatibility. But it's fundamentally the same experience. So you can go and run your console application, and the standard out of those applications gets rerouted over and integrated into Windows. But it's overall much better than WSL1. So when we talk about WSL, so that's been a feature that's been very popular with our developer. Like nowadays we have lots of developer that needs to go and do development on like many different platforms, and they have lots of tools that can only run sometime in Linux, or maybe run better in Linux than the Windows version. And some of the features that like developers have been asking us to is one, having access to the GPU from within WSL. So mostly for compute, like developer that wants to do like AI or machine learning. And in particular, the request has been hey, can we get access to NVIDIA CUDA to run their workload? But in general, things like TensorFlow, PyTorch, or any other framework. And how we go about adding the GPU inside of WSL, that's essentially going to be the subject of this talk. The second feature that's been requested from WSL is to go and extend WSL beyond a console-only experience and be able to allow like GUI application to run. And that's going to be the subject of our next talk on how we're going to extend WSL to be able to run X11 and Wayland applications. Okay. So yeah, so this talk is all about how do we basically bring GPU hardware acceleration inside of WSL. But before we dig into like the approach that we took and how we're implementing this, it's good to kind of take a quick step back and see how do we actually want to achieve that, right? So at the higher order bit is we want to go and share the GPU with the host. Like we don't want to go and dedicate a GPU to the host. Like, there might be a single GPU on the system and the host still need to be able to use that GPU. And we want to make all of the GPU that the host has available to the Linux side of things. And we want to enable essentially both process in Linux and process in Windows to simultaneously be able to submit work to the same GPU and let our GPU scheduler and our GPU memory manager allow both of them to go and use the GPU. So we want to enable also like flexible management of resources. And what this basically means is we don't want, for example, to do fixed partition of the GPU. So we have other GPU virtualization technology that we use, for example, in our Azure cloud that allows us to take the GPU and essentially like split it into like pieces and then hand off pieces to like various virtual machines. And then each of these virtual machines basically have exclusive access to that piece of the GPU. Well, on a client scenario like this, that's not really good. Like, imagine if our user is a student that may be doing some homework and some research project and needs to run under Linux, and then decide to take a pause and go play a video game. We want to make sure that, like, hey, as you launch the game, even if you didn't go and kill the virtual machine, the fact that the virtual machine is not really doing anything, it's mostly idle, we want VidMM to have the ability to go and take all that memory, send it out, give it all to the game so they can have a gaming experience. And as he's done gaming and wants to go back, at that point, we can reassign all the resources to whatever work he's doing inside of Linux. So essentially treat processes that are running inside of a virtual machine the same way that we treat a process that's running locally. And we want to enable this across a broad set of API. So we want to enable CUDA, we want to enable OpenCL, we want to enable OpenGL, and potentially like more API into the future. You'll see we'll talk about DX as well. So we're bringing DX12, but the way to think about us bringing DX12 is really as an implementation detail that basically allows us to go and achieve this goal of running OpenCL and running OpenGL by essentially creating layers on top of our DX12 driver. So that's a way essentially of bringing those API across a large number of vendor and a large number of driver without having everybody doing a large amount of work. So how do we actually achieve this, like sharing the GPU with the virtual machine? So we achieve this using a technology that we call WDDM GPU parallelization, or GPU PV for short. And to understand a little bit more about WDDM parallelization, I'll take a little step back and talk a little bit about WDDM, and then go into how parallelization works and how we're extending it for Linux. So WDDM stands for the Windows Display Driver Model. It's a really thin abstraction of the GPU, and you can think about it as like the lowest layer on Windows where all the various API are built on. So the role essentially of WDDM is to abstract the GPU in an API agnostic way and allow various API to do things like allocate memory and creating devices and submitting work to the GPU and things like this. You can think about it in terms of, on the Linux side, the closest equivalent would be like DRM and KMS. And parallelization essentially refers to the fact that the hardware that we use isn't actually built for virtualization. We achieve virtualization through software enhancement. And the level of abstraction in our parallelization is essentially the WDDM interface. We take that interface and that abstraction to the GPU where all of our user mode driver are built on, and we essentially project that into a virtual machine. And this allows the virtual machine to have access to those services, and then you can go and implement the same API. So we don't actually project the whole of WDDM. We project a subset of WDDM that is enough for what we call compute, or like, rendering engine and things like this. So we don't project, for example, display related things and other stuff of the sort. And WDDM parallelization was designed for exactly these kind of like scenario. And it's used today for hosting Windows guests in various scenarios. So for example, we use this for Windows Defender Application Guard, where we run the browser inside of a virtual machine for increased security. It's used in things like the Windows Sandbox. It's used in things like the device simulator. So if you're doing HoloLens development and you don't actually have an HoloLens, you can basically run our emulator, and our emulator provides GPU acceleration inside of the virtual machine that's running the emulator. And then the idea here is to extend that support for Linux guests. So in addition to running Windows guests, we'll now be able to run Linux guests. So what does the WDDM architecture look like at a high level? So at the very heart of WDDM is the graphic kernel. This is where like our memory manager, our scheduler for the GPU reside. And it's essentially the component in the Windows that is responsible for sharing the GPU and managing the GPU across all the various processes that wants to go and use it. And the graphic kernel works really closely with another component that we call the KMD, or the kernel mode driver, that's provided by our ISV partner. And the KMD, you can think about it as like the HAL, or the abstraction that we're using to actually touch the hardware. So the graphic kernel never interact with the hardware directly. We always do it through a DDI, through the kernel mode driver, and the kernel mode driver is the one that ultimately go and touch the hardware directly. And then the graphic kernel exposed to user mode what we call the WDDM services, or the D3D KMT API. And these are the API that, like the low-level abstraction API, that all of the high-level API or higher-level API are based on. So when you take something like a Vulkan or OpenGL, OpenCL, CUDA, or things like this on Windows, the API typically has a user mode driver that, in the case of OpenGL, CL, and things like this, we typically call ICD, or installable client driver. And that driver provided by the partner essentially goes and calls directly into these D2D KMT API to go and talk to their GPU. For D3D, it works something kind of very similar, where we basically run the D3D API, and we also have a user mode driver that, in this case, we actually call UMD, or user mode driver. You see often we actually interchange the name ICD and UMD, and we call them all UMD. But like the main difference with the D3D model is that rather than having the user mode driver call directly into like our kernel services, they basically just go and talk directly with the D3D runtime, and the D3D runtime manages talking to the kernel on their behalf. And the WDM services are really kind of low-level abstraction of the GPU that tries to be like API agnostic. So they do things like enumerating all of the GPU, being able to create a device on the GPU, be able to create context or hardware queues, be able to allocate memory, be able to go and map GPU virtual address to some of these buffer, to create synchronization object, to submit work. And all of this is in an API agnostic way. So for example, from VDM perspective, when it allocates memory, it doesn't really care if it is for a Z buffer for the 3D or whether it's for like a shader in CUDA. And then the goal of WDM essentially is to isolate process or like entity that are trying to use the GPU from one another, right? And as the process try to talk to the GPU, each process is isolated into their own GPU virtual address space. They can go and allocate their own memory. If process wants to explicitly communicate to one another, we have mechanism to create shared memory and shared sync object and things like this. But by default, the process is kind of in its own little bubble. And WDM essentially offer that ability to go and create like different environment that the GPU can run on, and all of these are like fully isolated from one another. And then VDM, for example, will decide like, okay, which of these is resident at the time, or which of their memory is resident, etc. So WDM is already designed to essentially allow multiple clients to go and use the GPU and get the GPU schedule like fairly among them. The idea of the approach that we took to share the GPU with a virtual machine was to take this WDM layer and essentially say, hey, we need to project that inside a virtual machine and makes the same service available. So that from the point of view of the kernel, a process, whether it's running locally on the machine or whether it's a process that is running inside of a virtual machine, it all basically look the same for the GPU scheduler and the GPU memory manager. So how does that work? So you can take it on the host inside of the Windows kernel mode. We're running this WDM GPU power virtualization, and it exposes an interface over the VM bus. It exposes a protocol that allows guests to go and have access to the GPU. This part is completely agnostic of the type of guest. So the guest could be various versions of Windows, it could be Linux. This is all identical. Like the host does not actually has to worry about whether it's talking to a Windows guest or a Linux guest or which version. Like this is a fully version interface. In the case of Linux, we essentially go and wrote a kernel driver inside of Linux that goes and talk over that VM bus to go and expose the GPU to Linux user space. And we expose the GPU through this new dev-DXG device. So we have to expose it through this because we could not expose it just as a, for example, DRM device. Like DRM, the model kind of expect kind of a real GPU that they control and things like that. Versus in our case, what we were trying to go and do is to go and say, hey, we want to bring these WDM services that allows software that was written against that GPU abstraction to be able to run inside of a Linux environment. So we have dev-DXG, and then dev-DXG through some magic in libdx core, we make the same WDM services, the 3D KMT API I was talking about earlier, available essentially inside of Linux. And this allows us to take like drivers, for example, like CUDA, and essentially recompile them for Linux to be able to go and access the GPU through that interface. So you can think about, like, for example, a driver like CUDA. The driver, like the major portion of the driver is already cross-platform, right? It's the same code that runs on Windows, that runs on Linux. And then the driver has a little like HAL layer that goes and deal with like the differences between the platform. And you can think about that HAL as being divided into two portions. So there's a portion of the HAL where the libcuda has to deal with the differences between, say, allocating memory on Windows versus allocating memory inside of Linux. And there's another portion that deals with how do you talk to the GPU itself. And in this case, essentially, what we worked with NVIDIA on is to go and say, hey, can you recompile your CUDA driver using your HAL to talk to Linux? But when you go for the OS, but when you talk to the GPU, go and use the WDM interface. And so that gives us kind of an hybrid driver that gives us, for application, the CUDA surface, but that allows us to run it in that environment. And then we did something similar with D3D12, where we ported our D3D12 on top of WDDM, and then we've asked our IHV partner to go and compile their driver. And this allows us to go and get more API by leveraging things like Mesa, and be able to go and create CL on 12, GL on 12 layers that gives us access to these API on top of this D3D12. This DXG kernel, like Linux Edition, is open source. Like, we have the code on our fork of the Linux kernel. And the two things that you should keep in mind for this kernel is that it's not a straight pass-through. We say like, hey, we're projecting the API. Yes, like fundamentally, there's the memory manager and the scheduler are fundamentally on the host. So there's auto requests we have to go send on the host to basically go and do. But you can think about some API are implemented locally, some API are implemented remotely, some implemented in a combination of both. The other thing is we also try to not do any data copy. So all the data that goes over the VM bus is essentially control information. Like, we try really hard to make sure that as, for example, the user mode driver goes and write a comment buffer, the comment buffer that's being written by the driver is exactly the comment buffer, that the same memory that the GPU is going to read from. We don't make external copy. So I'll just go quickly over to kind of show a little bit how we go about doing that, where, like, how do we give, for example, CPU access to like our GPU memory. So when we allocate GPU memory, some of that memory is going to require CPU access. So things like, for example, a comment buffer that the driver writes into comments for the GPU, or index buffer, vertex buffer, constant buffer, or all kind of buffers like that. So the way to think about it is on the host, we have this process called VMM. And this is essentially where we host the memory of the virtual machine. So if you have a virtual machine, for example, that has, 8 GB of memory, we just allocate like 8 GB of virtual address inside of that process. And then through the magic of SLAT, we basically project that, and that becomes the RAM of the virtual machine. That's what we call a VA-back VM. So even though the VM thinks it basically has a bunch of like RAM, like, that's kind of non-pageable, it's basically the RAM. On the host, that memory is virtualized. So like, we can page it out and do other stuff if it's not actually in use. As we load the Linux kernel, that's the RAM that it's running against. So when we initialize the XG kernel inside of the Linux kernel, it basically goes and take a range of addresses in the CPU physical address space that we're going to use to manage access to our video memory surfaces. So in user mode, or in user space, when you have an application that goes and asks for memory to be allocated, that request goes over to the XG kernel on the Linux side. And then that request gets sent over the VM bus, and VMM inside of the host goes and create that memory inside of the VMM process. And then through the same SLAT magic from before, that memory essentially gets projected inside of the WSL VM. So that once we go back to the Linux side of things, the DXG kernel inside of Linux can basically map a user pointer to that memory. So once that's set up, what user space in Linux has, it has access to the same underlying pages that the GPU is basically going to read. There's no copy of data or trap or anything like this over the channel. So if that surface, for example, is a comment buffer, these are the commands that the GPU is going to go and read directly. So that example is for system memory. But if, for example, you have VRAM, and for example, that VRAM is visible over the PCI bar, we basically have mechanism that allows us to kind of take that virtual address and map it back and forth between like a IO address over PCIe or like a system memory address. And we can even do that while it's actually being actively used. So even if you have, for example, a thread inside of Linux that is actively writing to a surface, and VMM decides, hey, I need to demote this surface from VRAM to system memory, we can, through this mechanism, essentially put the SLAT in error, so that or the PTE invalid, so that has the thread access it will pagefold. The pagefold handler will recognize that that address is being modified. Then we can go copy the data from video memory back to system memory. And then once the transfer is finished, we can refix up the PTE and then retry the access. And then the thread on the other hand will have kind of stop in default handler, but otherwise would not have noticed that basically the memory moved from one location to another. So this support is coming with WDDM 3.0. So all of our driver going forward will have built-in support for Linux. This is going to be validated as part of our certification process. So all of our partners are essentially adding systems that are configured for Linux into their test pool. And we have tests that goes and validate that like, yep, the driver works correctly inside of Linux. And the idea here is to really create an environment that out of the box, things already work. And now I'm going to hand it off to Jesse to go over the user space portion.
Thanks, Steve. I'm here to talk about basically what we have in WSL for user space graphics. So I just want to quickly reiterate some of the goals that Steve had talked about. Our goal is to support the breadth of existing Linux compute APIs, for example, NVIDIA CUDA, OpenCL. We eventually would like to have graphics APIs like OpenGL and Vulkan as well. We would like to make sure that we minimize any unnecessary or redundant work that our driver vendor partners would have to do. We want to support hardware-accelerated machine learning frameworks, for example, TensorFlow. And it's very important to understand that we are not trying to introduce any new competing APIs at this point. We're really just trying to support what already exists in Linux, your existing apps. When we approach the problem of how to get compute acceleration in WSL, we kind of saw two possible approaches. So the first one was to basically ask all of our driver vendors to port all of their ICDs for every API that we care about. It's a lot of work. The second option was to ask the driver vendors to port one graphics UMD, and then we could layer everything else on top of it. Specifically, if we ported D3D, then we could build layers to support all the rest of the APIs in terms of D3D. The ICD approach meant that we would have to continue to ask vendors to port new ICDs for every new vendor, for every new API that we cared about. So that could be at least 3 APIs across at least 4 vendors, where the mapping layer approach really means that we need one UMD from every vendor, and then one mapping layer per API. It's a much better scaling solution. It also enables us to leverage the DirectML backend that we have for ML frameworks, for example, TensorFlow. And it also helps contribute to Windows as well. We can continue to use these mapping layers to decrease the vendor burden of supporting Windows. It is still possible, of course, for ICDs to be ported. For example, NVIDIA's CUDA does work this way, as Steve mentioned. They basically just talk directly to the D3D KMT APIs. But in general, the approach that we think is more scalable for long-term graphics in WSL is to build mapping layers on top of D3D. So what have we done today? The lowest level piece that Steve already talked about, DX Core, provides some APIs for enumerating GPUs and querying properties. You can kind of think of it as roughly equivalent to what the DRM render nodes provide through their user API. We also have D312, libd312. It does require a D312 UMD to be present on the system. And at this point, we do have UMDs available or in development from all of our Windows GPU vendors. Actually, just a couple days ago, NVIDIA announced that they have a D312 UMD for insiders as well. And basically, this is the same D3D that we have on Windows. Layered on top of that, we have DirectML, which is a machine learning framework, a layer on top of D312 that helps provide highly optimized GPU-accelerated ML operators. And on top of that, we have TensorFlow, which is a widely used ML framework. We have a DirectML backend for TensorFlow available today. So some comments on the things that we've already built. Like Steve mentioned, all of the stuff that we're talking about, even though we call it graphics, we are mainly just focusing on compute acceleration. And when I say compute, I'm not trying to say that you can't do rasterization or you can't do, for example, ray tracing. What I really mean is that there's no window integration. So you can do rasterization, but you're not going to be able to see the contents unless you pipe it out to a file or do some other way of visualizing it. Just to reiterate, the intention of D3D in WSL is really as an implementation detail for GPU acceleration. It is really just to host other mapping layers for existing APIs on top of it. We are not trying to introduce a new API for apps to target directly. We don't have any plans to ship an SDK for D3D and WSL. It's really just an implementation detail. Yeah, it's really only there to allow higher level frameworks and APIs to use it. The D3D stack is the exact same code that runs on Windows. All components involved were modified, like Steve mentioned, just to dual compile. So it's basically the exact same thing. We fixed a lot of non-conformant code while we were doing this. As I'm sure some of you already know, the MSVC compiler is not necessarily conformant, and we had a lot of code that relied on that. So this was actually a great exercise for fixing a lot of that debt. As part of this process, we went ahead and replaced a bunch of Windows-specific constructs, like critical sections, for example, with cross-platform code, heavily relying on STL and C++ runtimes. We basically wrote a header shim that kind of replaces Windows.h so that we don't have to rely on the Windows SDK. And it provides roughly compatible defines and type defs to what our codebase and API expects. So for example, the D3D API has all caps uint, for example. We provide a type def for that maps to something that works roughly the same on Linux. And we are we're cross-compiling with Clang. And this process actually caught several real bugs because Clang's warnings are significantly better than MSVC's. So this was, again, a great experience for improving the quality of our code. A few notes about TensorFlow. It is TensorFlow on DirectML. One of the primary reasons that we went ahead with a DirectML version of TensorFlow for WSL is that it runs on a wide variety of hardware. If you wanted to use CUDA for compute, that would only run on NVIDIA. If you wanted to use, for example, ROCm, that would be a limited set of new AMD hardware. But with DirectML, we support all of our vendors. And not only do we support them, we kind of provide a guarantee of consistency and conformance because we test and work with all of our hardware vendors to make sure that we provide consistent results across all of our vendors. It's easy to set up. You just do pip install, and then you have TensorFlow with DirectML. And it is now open source. We've been working very closely with the TensorFlow community to bring this code upstream as well. At this point, we currently only have a fork of it, but we would like it to be available in the official builds of TensorFlow going forward. So something that's a little bit kind of interesting and unique about what we're doing here, most code on Linux ships as source, and it's expected that each distro kind of compiles their own source. We are shipping binaries. So we are doing our best to be distro agnostic with how we do this, across both Microsoft Code, D3D and DirectML, and the drivers that our IHVs are providing. Basically what we're providing is not quite statically linked binaries, but as close as we can get. So really the only external dependencies that we have are on the C library. Everything else is statically linked, so the C++ runtime, and any other dependencies that we have. We are making sure that we don't have any exceptions crossing module boundaries, for example, so it shouldn't really matter, what we're linked against versus who's calling us linked against versus what the drivers are linked against. We are technically linking against muscle in our build, but we're doing it in a glibc compatible way, and as far as we have been able to test so far, it does appear to be giving us binaries that really do work in a wide variety of distros. At this point, our primary target is glibc-based distros, but we would like to make sure that we support everybody to the best of our ability. So what is next? Some things that don't exist yet. We've already mentioned that we would like to bring OpenCL on 12 and OpenGL on 12 mapping layers, both of which are heavily leveraging Mesa for their compiler and runtime infrastructure. At this point, we have both of these working on Windows, but we haven't yet started any efforts towards getting these working in WSL. And OpenGL specifically, if we wanted to get window integration, that is a very hard problem to solve. There's a lot of open design questions about how we do that. Not intrinsically due to the way that Mesa or GL is structured, but just it's a hard problem to solve because our DevDXG graphics acceleration is not quite the same as what is already expected by Mesa, but I think that is a problem that we can solve. And there is already some work underway in getting GUI integration for WSL in general. So the next talk that we will be doing is Steve talking about our plan for getting non-accelerated Windows system integration with WSL. That is the X11 and Wayland applications in WSL talk. And I do have a quick demo. So as you can see, this is basically a WSL terminal that is running TensorFlow. You can see that Task Manager is running next to it, showing that it is running on an Intel device, and it is heavily leveraging the GPU, which is something that it wouldn't be able to do before this integration. And then some more info on how to try it out. You can check out aka.ms/GPU and WSL docs for more information. And that's it. And now we can open up for questions.
Okay, we should be live.
Yep.
So we have wait a second.
Is there a problem?
No, it's just I'm hearing myself. Okay, so I just took out the headset. So we have multiple questions. The first one from Robert Fox. Is there an entirely open source software user space tag? I guess it's made from the WSL-DX, the kernel driver.
At this point, no, we don't have a full open source stack. I guess there's still some echo going on. I don't hear any echo on my side, though. Yeah, at this point, we don't have any open source user space, unfortunately, but that is something that we are looking at. We're trying to work with our vendors to get an open source user space with on top of DebDXG.
Very good. Next question is
Steve, I think you're trying to talk and you're muted.
Yeah, sorry. Yeah, I was just saying we have like partially open right now because like all the Mesa part up to DX is open. But then after that, DX is closed. But yeah, like Jesse was saying, we're looking at to see if we could get some API to be like fully open, to have at least one example.
Sorry, could you just keep on reading the questions? I'm gonna try to fix this echo.
Yeah, sounds good. Let me take a look again. Next question was, is WDDM GPU scheduling also closed source? And yeah, at this point, the GPU scheduler portion is hosted on Windows. So that is currently part of the Windows kernel and is closed source. Next question, the slides on an overall architecture will be available after the talk. And yes, we're planning to upload the slides to the X.Org website after the talk. Next, this is not for gaming, just to clarify. At this point, we're looking at compute, machine learning mainly. Next question from Robert Foss. Could DXG kernel conceivably be built as part of the Linux DRM subsystem? That way other Linux drivers could take advantage of APIs like DirectML. We are interested in upstreaming the DXG kernel that we've built so far. Right now, the DXG kernel that we've built only acts as a paravirtualization driver on top of a Windows host. It is not a self-contained GPU scheduler. Though potentially building something like that is possible.
Yeah, the key thing with DevDXG is really about trying to share the GPU with the host. So that's why we built kind of like this separate infrastructure to be able to do that. Like we did not see a way where we would be able to build this as a actual like DRM driver. We could have used a DRM driver if we had done something like discrete device assignment, where we take the GPU and just assign it to the VM, right? But then the host doesn't get to use it anymore. Or if we had like what we call GPU partitioning, where we can slice the GPU like in virtual function and assign a virtual function. But again, resource management wise, that's not very nice. Plus today, like the hardware is only on server class hardware that have this support.
Next question. What is our long-term goal for this project, and how much of it can be upstreamed? Steve, do you want to start?
Yeah, so basically the long-term goal is to really make WSL an interesting part for developer, right? So that like folks that need to go and use Linux and need to go and use Windows to not have to deal with 2PC or reboot or anything like this. So to be able to do as much Linux stuff inside of Windows and be able to kind of bridge the gap between the two. WSL has been around for a little while. We see this as really, really critical. Like, although it's for kind of a small number of people, like, my mom will never go and run that. It's for developer, and we see developer as like really important, like the whole like Steve Ballmer, like developer. So it's about making like this environment better and better. So the GPU is really critical. And then we're bringing GUI app, and then we want to put it all together.
And how much of it can be upstreamed?
Yeah, so we're hoping that like all the pieces can be upstream, so it can basically be like completely open. There are things like DX, like there's some of us that would love to make it like open source. That's a more difficult discussion, maybe one day. But like all the pieces, like you'll see later, like all the Weston and things like this, like changes that we're doing, like it's all going to be open source. Our vGPU projection, anything that's on the Linux side of things, except for like the little DX piece, is going to be open source.
Next question is, can we know whether we have plans to support AMD ROCm compute stack for WSL2?
Yes, I don't want to talk on behalf of AMD. That's more of a question for AMD. But you can imagine, given CUDA is there, there's probably interest from like other competing compute API to kind of do the same.
Yep. Next question, can the per-virtualization that we created be used independently of WSL with just any VM?
Short answer is yes. Like, any VM, like any VM hosted by Windows, because it's fundamentally built on like on Hyper-V and VM bus and things like this. But yes, you can use this in a like Hyper-V VM, for example. You can use this on an HCS VM. The main thing is if you go and use it in an Hyper-V VM, then there are certain things that you kind of have to go do like manually. Like we don't kind of package it all up like automatically for you. Like, so for example, if you install like a version of Linux inside of an Hyper-V VM, you won't automatically get the libdx core, libd3d. They're going to be like on the host. You can go get them from the host, and then you can copy them inside, and then that will give you like the bridge necessary to go and run like our various layers. Versus in WSL, we kind of do a bunch of magic where these files from the host are automatically mounted and map into the right place. So like as we create the VM and instantiate user space, everything is already set up and working. Versus if you do your own VM, then you kind of have to piece things back together. But if there's interest on this, we can share like the recipe, because most of our development was actually done that way originally.
Yeah, and the other thing that I'm going to add to that is one of the primary reasons that we're interested in upstreaming our DXG kernel Linux driver, is so that you can just take an off-the-shelf Linux distro, and it has this per-virtualization driver built in, and then all you need to do is set up the user space correctly. Next question, do we intend to also support ARM 32 and 64-bit? Yes, at this point we do have plans for ARM 64.
Yeah, ARM 64 only.
And that's all the questions that we have so far. And I guess we're actually just about out of time as well.
Well, we still have like 32 seconds. So is the echo fixed now? Everything is fine.
For me now.
I mean, I don't hear myself twice. That helps a lot. And then apparently the cathedral is also gone, which I guess is a bit sad, but we'll deal with that later. Okay, well then, thanks a lot, and see you again in 10 minutes.
Sounds good. Thank
Yep.
you.
Okay, well, thanks a lot.
Yeah, thanks.
Yeah, thanks for hosting.
Hi, my name is Steve Pronovost. Today I'm happy to talk to you guys about new technology that we're bringing to WSL called WSL-G, which essentially will enable you to run X11 and Wayland application within WSL. So what is WSL? WSL is the Windows subsystem for Linux. In a nutshell, it's an infrastructure that allows you to run like Linux application inside of Windows. If you want a little bit more detail about WSL, there's a lot of information out there, and you can also look at our other talk that we did earlier on WSL graphic architecture. The key thing with WSL today is that it's a terminal-only experience. So you can run Linux application, but only console application, and then standard out basically get redirected over to Windows. So you can run Linux inside of a terminal. The most requested feature for WSL has been twofold. One, getting the GPU inside of WSL, and that was the subject of our other talk. So I would invite you to go in and take a peek at that. And the subject of this talk is the ability to go and run GUI application. Whether it's your like favorite editor or like some tools that you must absolutely use. There's been demand of being able to go and run these applications inside the WSL. But wait, people can go and say, hey, yeah, but you can already run X11 application in WSL today. So for example, you can go and run an X server inside of WSL, and then you can run an X client on Windows. And there's a lot of instruction and very useful YouTube video that goes and show you like how to go do this. And I think even like Penguin distro kind of has this like all built in. It works, but it's not a really great experience, because fundamentally what you have is a desktop in a window experience, right? Like you don't have an integrated desktop. What you have is you have your Linux desktop, you have your Windows desktop, and you have to kind of go back and forth and potentially scroll. With multi-mon, it doesn't work very well. Performance is also not great because fundamentally all the bits are kind of copied over. There's no Wayland support. Like Wayland only work locally. There's no support for over the network. And it doesn't generally work out of the box either. So you have to kind of go out of your way to do this. And essentially what we wanted to go do for WSL is bring kind of true integration into Windows so that you can basically have a desktop like this where you have some application that are like native Win32 application that runs on Windows itself. And you have Linux applications that are running inside of a virtual machine and are being remoted over, but all of those details hidden from the user so that it just looks like a unified desktop. And for example, in this picture, I'm running like several Linux applications, including the browser that you see there. That's actually the Google Chrome, but the Linux version, not the Windows version. So that's kind of what the experience we want to go and achieve. So what's our approach? So we looked at like different way of doing this and what other folks had done kind of similar. We fundamentally decided to build on top of Weston. Weston, for folks that are not familiar with it, is essentially the reference or simple compositor for like Wayland. And the idea was that Weston already supported the ability or already had an RDP backend where you could basically run the Weston desktop and just remote it to another PC through this RDP. In a nutshell, what we're doing is we're taking Weston, we're taking this RDP backend, and we're extending it to teach it how to basically do remote application. So instead of remoting the desktop, we remote individual window, and then we can take those windows and integrate them with the rest of the Windows desktop. And you'll hear me refer to two things in particular. There's something we call RAIL, which stands for Remote Application Integrated Locally. This is essentially something we've been doing for many, many years, and it's part of the RDP protocol. It allows us essentially, like the name state, to remote an application and to integrate it locally into your desktop. And then we have a variation of this called VAIL, or Virtualized Application Integrated Locally. The way to think about VAIL is that it's RAIL, but because we're inside of a virtual machine, and like on side of a virtual machine, we can play other trick. We don't have to go over the network. We can like share memory between the guest and the host. We can have essentially a more efficient protocol to kind of move bits between the client and the server. But outside of that, it's the same. It's the same concept. So that's for graphics. So for pixels, we're using essentially Western. And then for audio, we're running Pulse. So we're running a Pulse audio server. And then we wrote some like plugin to Pulse that allows us to take the audio and essentially like shuffle it to like our Western compositor. And then Western can take that audio and like mix it over like the RDP channel and send that over to the client. And similarly, like if the user is running a microphone on the host, RDP already support taking the audio from the microphone, sending it back to the RDP server that's running inside of our Western compositor. And then we can take that audio and reshuffle it back to Pulse so that we can have both like audio in and audio out. And all of this is being built with the intent of being able to like contribute back. So it's all open source. Like everything that we're doing in RDP, it's all documented. Like there's protocol documentation you can go and look at. And there's no secret sauce or anything like this. Everybody can redo exactly the same thing that we do here. So here's kind of a quick overview of WSLG. So at the heart of it is basically the Western compositor. So the Western compositor support multiple shell. So it already has like something called a desktop shell. It has an IVI shell like for automotive. It has also like a full screen shell that is used for full screen app, like kiosk type application. And so in our case, we basically wrote a new shell that is geared toward remoting app, because in our case, we don't really have a shell/desktop. We don't draw a widget or anything like this. It's really about capturing the content of the top level window and remoting this over. So there's a couple of different rules that our shell has to basically follow. And then Western open like a Wayland socket that allows like native Wayland application to connect to it and run. And we also run the X Wayland server that basically give us like an actual X server, so we can go and run X11 application. So we're running X Wayland in rootless mode, so that basically all of the X application are being rendered by the X server, and then the X Wayland take those output and forward them over to like our Western compositor. And then inside the GAS, we're also running a Pulse audio server that's hosting our RDP sync and RDP source for audio in and audio out. And we forward those over to our compositor, where we're running the RDP backend, but we're running a greatly enhanced RDP backend. Like, so we added support for things like, for example, multi-mon. So now, like, you can go run all of this in multiple monitors, and as the monitor comes and go, like, the application will see the monitor comes and go. And added support for things like cut and paste and things like this over like the RDP channel. So we start essentially to have an RDP server that is like fully functional. That allows you to do like almost the same thing that you can do, like say remoting into a Windows box. And on the Windows client, we're essentially just running one of our existing RDP client. In particular, we use MSTSC, which is probably the most known RDP client. We're using a slightly modified version of MSTSC that's gonna ship with Windows. There's a couple of small little things we had to go in and tweak. But for the most part, it's basically the same client. So why base this on RDP Rail and Vel? So there was really kind of like at a high level two different approach we could have looked at. There was kind of like the Google approach, where they decided to basically just go and remote the Wayland protocol and then run a Wayland server or Wayland compositor on the host. For us, we don't really have a Wayland compositor on the host. It would have been, hey, rewrite like a Wayland compositor from scratch. What we had instead was basically like that same kind of technology of like remoting application we had technology already like really mature around that, right? Like with RDP, we've been remoting application like this for many years. We have really big business built on top of that. So today, for example, we have this thing called Azure WVD or Windows Virtual Desktop, where you can go and run application in the cloud, and we just go and remote those applications, not the whole desktop, but just those applications, and integrate them onto your desktop so that you can have a PC where some app are running locally and some app are running in the cloud. So technology that we understand well, we understand the security around it. And it was very interesting for us to kind of build on top of that, because it gave us basically both the, hey, we can reuse a lot of that client, we can reuse a lot of that experience, but it also basically allows us to kind of remote both X11 and Wayland in a completely like invisible way. And then if you're over a true network, but then we go and use something like the Rail protocol. If you're over a VM boundary, then we can go and switch over and use the more efficient Veil protocol over the VM boundary. And it's all documented, open source, and it was giving us kind of a good way to contribute back to Weston and make it kind of a real shipping environment. So the thing that's important to realize is the way we built this, we built it for really remoting transparency, and we did not build this specifically for WSL. So yes, we're running Weston inside the WSL, and in this case, we're veiling the application out and integrating them into the desktop. But it's not specific to WSL. You can, for example, spawn an Hyper-V VM, go and run Weston in it, and you'll be able to veil out of that VM as well back onto Windows. But if you want, you can also just run Weston on a like Linux PC. And in this case, we can connect over TCP, and you can basically rail the data out. And that's something that we do during our testing, where like on my dev box at home, I have a little Raspberry Pi, and I go and run the Weston compositor on the Raspberry Pi, and then I can basically just like TS into it, and I can remote application running on the Pi back onto my desktop, and I get the same experience that I do out of WSL. So there's really nothing specific about WSL. It's really about building a full-fledged RDP server in the backend of Weston, as one of the backend for Weston. And this approach, one of the nice things is, if, for example, there was ever a demand to go and say, oh, we would like to go and run some of these Linux applications, maybe like the same way as we do for Windows with WVD, maybe we could run some of these Linux app in our cloud, and then we could just go and stream them to like devices using the same model that we do today. So that was pretty appealing. So it gives us all of these niceties. Okay. So how does that fundamentally work? So the very first thing that we do essentially when we establish the RDP connection in Rail is we have to mirror the desktop. So for example, if you have 3 monitor oriented a certain way, we're going to basically mirror that exact position of the monitor inside of the virtual machine. And that's important because whether you're trying to remote application, a Win32 application on Windows, or whether you're trying to remote X11 application in Linux, X11 app are basically aware of their placement on the desktop, right? So they have to be aware, like how many monitor is there? Where am I on a specific monitor? So in Rail mode, essentially, we always mimic things. So as we initialize, I have a little picture here. As we initialize, if we have 2 monitors, we'll basically open RDP connection, send that configuration. So that will initialize like, the WL output to map exactly. So you'll have the exact same monitor at the exact same resolution, orientation, position, like all that stuff. There's a little bit of goo with like coordinate system, because the RDP desktop has a certain coordinate system. RDP input has a different one, and Linux has different one. So we do a little bit of shuffling to get the coordinate to match. But then the idea is like, as the desktop changes, so for example, if the user go and change the resolution, then we send that information over and we go and reflect it. So that basic, and then we reflect it back to client as well. So that essentially, if you use a tool to look at the X desktop, you'll see that it always essentially map to your configuration of your Windows desktop. And we've taught like Weston how to deal with like monitor arrival and monitor departure and like monitor changing resolution and things like that. So that it just works today. And then once we've established our desktop so that the Linux environment and the Windows environment have desktop that kind of look like one another, essentially what we're doing is we're proxying the top level visuals, right? So whenever like you have like a, for example, visual that gets created or say a surface, a WL surface in Wayland that gets created, over the RDP connection, we basically go and ask the RDP client to go and say, hey, can you go create a window of this size at this location? And then whenever, like, for example, there's an update, so if there's an area of the surface that gets damaged, that damage area basically gets sent over. That piece of like how we send damage, that's the piece that's going to change the most based on the type of connection that we have. So for example, if you're connected over something like Rail, where we actually have to copy pixels, then like, we'll have to copy because we're over like a physical connection, maybe like a TCP connection or something like this. So we have to physically copy pixels. If we're over, like say a VM boundary, then we don't really have to copy things. We can basically just play like memory management trick and share surfaces. So yeah. When surface gets destroyed, it basically destroyed gets sent over. Move resize a little special. We actually have two versions of it. So when you have like raw input, you just send the input over to the host. To the guest. You let the guest handle the input, and the guest may decide to move the surface. And as the surface moves, basically there's a message sent back to the client to go say, hey, this window has moved, please update, and then it updates. We also have a variation of this that we're playing with, where we can do all of the window movement locally in on the guest. On the host, that allows basically for like smoother window movement still. But in the demo that we're going to show a little bit later, we're using the server-based move. So how does it work to send all of those dirty? There's kind of like three big paths. So the first one is, for example, when we're actually running Rail. So that means we're over a connection, like maybe like TCP or something like this, where the machine are physically disconnected and we have to copy the pixels. So in this case, we have what we call a composition beat, like the same composition beat essentially that Weston already uses today to compose the desktop. So you can think about it in terms of that you have your like Wayland app or like, XApp through Wayland that is sharing buffer with like the Weston compositor. And then there's a composition thread that like on a timer wakes up about like every 60 hertz. In this case, like for example, if you're on a remote machine, it's actually going to be like on a timer. If you're on a local machine, we can actually go use things like, the actual vsync of the monitor. And then the idea is like, hey, as that composition thread hit, like whatever has been made dirty during the last period is being sent over the network, and then it's being received on the Windows side, and then we go and upload it to like the proxy visual so that they always kind of remain in sync. So that's if we're like over the network. When we're over like just a VM boundary, then we automatically switch over to like Rail extension to the RDP protocol. And in this mode, essentially what we do is we have these shared buffer that come from the application that are shared with the compositor. Through some other magic, we can make those buffer essentially visible directly to the host so that the host has access to the same memory. And then when we have damage area, instead of having to kind of copy this over to the host, we can just send that notification of the damage area to the host. And the host essentially will take that damage area and upload it to the real surface. So in this case, for example, if your GPU only support the X11, what we'll do is we'll take those damage area, we'll copy that into like a staging surface for the GPU, and then we'll ask the GPU to copy from that staging surface into the final like swap chain for the window. We call it the comp swap chain. And then at that point, the data is now visible to like our compositor. And then our compositor can decide to either use it to composite a new desktop, or it can basically go and use the display to directly display from that surface with no other copy. But essentially, you end up with 2 copy compared to, say, if the application had run natively on Windows. If you have the X12, the X12 has this nifty little trick where it leverages like support in VidMM to basically wrap surfaces around existing memory. So we can go and create a heap like directly around the staging buffer that we receive from the guest. So we don't have to do that first copy. So now we have a staging that is basically directly onto the buffer that we've received. And then in a single copy, we can basically get this into the decomp swap chain. For software rendering, that's really kind of like the best we can do, because the software renderer, like, had to render to like system memory. And then on Windows side, once you bring things onto the GPU, well, you have to do at least 1 copy to get the data onto the GPU memory to be used. So it has basically damage, application that cause damage. We basically just forward those over to Windows, and it just adds a little bit of latency, but we no longer have to do this like beat every 60 hertz, like this. And this is feasible for a scenario, I should have probably mentioned that before, but this is for a scenario where we're using software rendering, right? So we're working on getting GPU acceleration, and Jesse's has a talk following later that talks more about how we're bringing support for GL and CL accelerated. But we're still going to end up with a lot of GPUs that just don't have a driver updated to support Linux, and we still wanted to be able to support those platforms as well. So our support for GUI application run with both on platform that don't have a virtual GPU and where all the rendering is done in software, or on platform that have a virtual GPU, in which case you're going to have accelerated GPU. So in this case, this is a software rendering. We end up with like 1 extra copy from running the application locally, and it works pretty well. The demo that we'll do later isn't actually quite that. It's kind of in between the first slide and this one. So yeah, and then to achieve 0 copy, we really need to have the vGPU. So with vGPU, what we're working on enabling is essentially the ability for application that use EGL or GLX to go and leverage a hardware acceleration through Mesa and through like the 12 driver that we've exposed. And in this case, the buffer that are allocated by the application and share with the Linux compositor are actually video memory buffers. So they're not like system memory, they're actual memory like on the GPU that the application can go and render directly on. And those buffers are basically shared with the host, like our DHG kernel, our WDM privatization projection of the GPUs allows us to share surfaces between the guest and the host. So those buffer can also be accessible directly like from the host. So on the host, we reopen essentially the same memory. And then what we can do is like the quote-unquote window on the host side isn't really a window with like, its own memory and things like this. Instead is what we call like a decomp visual. And it's basically just kind of a little pointer to like a swap chain. And we can take that swap chain that was shared by the guest, and we can basically just like hook it up to the visual tree. So the compositor essentially consume those buffer directly without introducing extra copy or anything like this. So we don't yet have that up and running on Linux. That's what we're working toward. But we have model like this running Windows on Windows today. And that gives us a kind of a nice 0 copy where like there's very minimum amount of overhead. Essentially, as you have a damage, we send the damage over. And like, I put like 100 microsecond of overhead for transport. That's really like usually on a fast CPU, it's actually like less than that. But, if you have a not too fast CPU, that's about the right order of magnitude. Okay. So that's for Avail and kind of like roughly how it works. How are we actually packaging this and getting this to work inside of Windows and like servicing it? So we're introducing this concept that we call the system distro. So if you're familiar with WSL2, we essentially have this Linux kernel, And then against the Linux kernel, we go and run different like user distro. So, and we're introducing this concept of the system distro, which is essentially a distro that we package together that has like all the components we need. So it has like Weston and X11 and Pulse Audio, and it has all the dependencies that it needs, but it runs kind of isolated from the user distro. And we just project like the various socket and environment variable, etc. the user distro needs in order to connect to it. It's sort of like a container, except that we don't actually use a kind of container like a Docker container or something like this. We're really running in like an isolated like mount and PID space. And this allows us to make sure that like, you know, a user doesn't accidentally like change a dependency and all of a sudden like things break on it. It just always works. And each distro, because WSL allows you to run essentially multiple distro against your kernel, so you may install Ubuntu, you may install Debian, and they're going to run side by side. Each of these distro gets their own instance of this system distro. And each of the system distro has an RDP connection back to the host. All of this is kind of like invisible to the user. The user doesn't really has to know. It's just that, hey, I just launched my user distro, and look, there was a Wayland server available, and there was a X server and a Pulse server available, and they just happen to work. Yeah. So in terms of servicing, all of this is actually shipping out of band. So it's not shipping as part of Windows. It can be updated outside of Windows, like release cycle, which makes it really interesting for us to be able to kind of update this quickly. It's kept always up to date. There's really kind of two ways to do this. So if you just want to let Windows do it, you can go into the settings, Windows update option. You can go and say, hey, just have Windows update stuff for me, and we'll just take care of it. We'll update it for you, and you don't have to worry about a thing. Or users that want to be under more control can decide, like, no, I'll decide when, like, you know, I pick update. And then we have this really nice just command line from a command prompt. You just type WSL -- update, and then that's going to go and put whatever latest, install it, etc. Once WSLG comes into our Windows Insider pool, that's how people will go get it. When you go into WSL update, at some point, boop, it's going to show up, and boom, you're going to have GUI application supported all of a sudden. So the system distro itself is read-only. So it's all packaged up, all read-only. We don't want user to put files there or things like this, because the servicing model is essentially like we download a new one, we throw away the old one, and then you start running on the new one. Actually, like we have this concept of a rollback, so we kind of keep the last one as a rollback just in case something goes bad. You can always go back one. But the idea is a replace, not some kind of like, oh, we'll merge the files that you had locally with the files incoming. It's like we throw away the whole thing and replace it all. So because of that, we don't want the user to go in and put things into it, because we would essentially like lose that data on update. But what if the user want to go and run a custom distro, doesn't want to run the one that we're providing? So for that, we're actually giving a way for user to go and say, hey, if you really want to go and build your own distro, and this is what you want to use instead of using ours, totally. You can just go build it, and you can change the WSL config option, and you can go in and run your own. All the code necessary to go and build a system distro and instruction to build a system distro is all going to be public. So anybody can go and kind of build their own. The fact that it's read-only for us is really just the, hey, this is how we're going to update our default. We don't want to screw it up and lose some of your file, right? So please don't put your file here. And if the user is using a custom distro, when we do the update, we'll only update the default system one. We're not going to touch the user one. So the user can go in and do their own experiment and build their own things. And the idea is that, yes, everything works out of the box, right? So you just go and enable WSL, like as you installed it, you go to the Windows Store, you go in and download one of the WSL distro, maybe like Ubuntu or Debian or something. You install it, and as you launch it, everything just works. Like you can just launch a GUI app, and you don't have to worry about how that worked. The Linux application appears in the start menu. So in particular, if you have application that have a .desktop file, we have a little agent that goes and enumerate those, and will go and reflect those and add those to your start menu. So then from the start menu, you can just go and click on those and it will launch like WSL, and will go and launch that application, just like as if you had a, if it was a local Windows application. And what if you don't want to use this because you actually prefer to use like an X server and client, like maybe you were doing today? That's totally fine. You can go into the WSL config and you can go disable WSLG, and then you can keep today's behavior if you want to. Maybe you just happy with console and you just don't want this, and that's totally fine. And a preview of this is coming to the Windows Insider pretty soon. I can't give you an exact date yet, but soon. So we'll end with a little demo of how that looks like.
Hey, Lior.
Hey, Craig. How's it going?
It's going good. I'll see you later.
Okay, we are now in the Q&A section. So, is Jesse here? Yes.
Yes.
Would you like to start summarizing what has been discussed in the QA channel, and then we can move forward with other questions?
Yeah, I'll go ahead and field some of these that we've kind of already talked about to Steve, and we can summarize. So first off, questions that were kind of answered in the slide presentation just before we got there. Do we have plans to support zero-copy buffer sharing? Yes, we talked about that a bit. Do we get 2 Weston instances for 2 Linux apps? No, you get 1 Weston instance per distro that you're running. The question of does drag and drop work? And asked a couple times. Basically, not yet. We'd like to. Copy and paste does work though. Question of is it basically just the RDP backend for libweston that is new on the Linux side? Steve, do you want to
Yeah, no, it's a little bit more than just the RDP backend. The RDP backend is where most of the changes are for Western, but we also had to change the shell. So Western already is built with multiple shell. Like, there's the IVI shell for automotive, the desktop shell, the full screen / kiosk shell. So we added another shell for remoting app. So some of the rules are a little bit different and things like that. There's also some changes to like the window manager and to libwestern itself and things like this, to like some small pieces we're missing. But generally those are pretty small. Like the bulk of the changes is in the RDP backend.
Next question was, do we have plans to upstream some of this work? And yes, we mentioned we're planning to upstream all of this. Questions about whether or not the RDP protocol was documented. There's some links in the Q&A IRC indicating yes, the RDP protocol is extensively documented, with the exception of the Veil extensions, which we are actively working on documentation for.
Well, I guess we could move to LinkMob's question. So, have you tested this setup with FreeRDP running as the client side? It sounds like I could use it for remote Linux to local Linux integration locally, smiley face.
So we have not recently did it. Like early on, we were actually using FreeRDP also like on the client until we fixed a few things in FreeRDP to actually make it work correctly with MSTSC. So since then, like we haven't run very much with FreeRDP as the client itself. But like eventually, yes, like the goal would be to be able to like this is just an RDP server, so you could connect to like any client as long as like you support like the Rail protocol and these things. But FreeRDP does.
There's one more question that we discussed earlier that I want to throw out there, which is the question of WL subsurface. Steve, if you want to talk about that.
Yes, like for subsurface, at least for our V1, the plan is to basically flatten them inside of libwestern. So to basically make them look to the host as just a regular WL surface, don't know the difference. Eventually, we may decide to go and extend the RDP protocol to be able to just send the subsurface and their like relative positioning, etc., so that we don't actually have to essentially introduce a copy or like a flattening inside of libwestern. But at least for V1, that's going to be okay. Right now, we haven't found a lot of application that actually uses subsurface because we don't actually handle them like very correctly and like almost nothing broke. But before we ship, we will have like support for them.
Very good. Just a comment from Timur, who says, "Good work, guys." Then Simon Sir is asking, how do you handle X11 creating new windows for sub-menus?
That's fine. Like the composer doesn't really care like what kind of window they are. Like it's like a visual is just a visual. If you create like any type of visual top level on the X side or Wayland side, those get basically remoted over and they get put into the exact same location. So that's why in the presentation I was talking about like the way that Rail works, the very first thing that we do is we mirror the desktop, right? So your X11 desktop looks exactly the same as your Windows desktop. The same number of monitors, same orientation, same position. If anything changes, we reflect it immediately, so they're always in sync. So application knows where they are, and if they create like a menu at a specific location, well, on the Windows side, when we proxy that visual, it's going to be at exactly that location as well. So things translate.
Okay, and the reason why Simon was asking this is because some X11 apps do not set the parent-child relationship correctly. But apparently it's not impacting you in any way.
Yeah, like we'll see. Like there's still some issues right now where we're trying to track down, but in general, it shouldn't matter whether there's a parent-child relationship. If you're like independent window and you kind of position yourself at a specific location on the desktop, you'll be on that specific location on the desktop on Windows as well.
Very good. Then Micro Hobby is asking, will Microsoft work on the Western style decorator?
What do you mean by Western style decorator?
Now comes the problem with the asking through IRC. I guess what he meant was the server-side decorations.
You mean like, for example, like the window looking a little bit different?
So
because like for X, like the window manager inside Western goes and render like the non-client area of like the windows. We're not looking at like changing it and trying to make it look more like Windows. Like we're kind of happy using it. Like your window will look a little bit different, but there's a lot of window anyway that basically just go and render their own non-client area. So things already look a little bit different. If you look at a Notepad versus Teams, for example, they already kind of look different.
Okay, well, yeah, but I guess that was the question, and apparently he's not been doubting that I was wrong. Oh no, he said yes, so I guess that was the question. Okay. Did you have to modify also the compositor of Windows to fit this these changes?
The compositor of Windows, no. Like, so we're using basically like MSTSC, like on the host. It's the same as MSTSC that we've been using for forever, that you used to just TS onto a machine. We did some changes to MSTSC, but they're very minimal. They're things like, so for example, when you launch WSL, we automatically go and launch the system distro, launch the compositor, and connect over RDP so that you don't see anything and everything gets like set up. So by the time you launch the first app, it just immediately pops up. Like there was not a way, for example, to establish a connection with RDP without them popping up a menu to basically go and say, hey, we're establishing a connection, wait a little bit. It's like, well, we didn't want that, right? So we added, for example, a silent mode to it. So various kind of little things like this to kind of polish the experience and kind of make it better, but nothing kind of really big and functional because RDP already supported like concept of like remoting app and Rail versus Veil.
Okay, well, it seems like it was the last question. So, well, we are 3 minutes and 30 seconds early. So, if someone really...
I was going to say, if we do have time, there was an earlier discussion around DRM buff and zero copy and MPO planes that Steve might want to talk about a little bit.
Yes, so to get to zero copy, with vGPU, we intend to get to a true zero copy, so we can share the buffer all the way from, say, and, share the buffer like with the host, and then those buffer are directly consumed by our compositor. So and our compositor basically has kind of like two mode of operation. Oh, sorry, my video just froze.
It's okay, at least your sound is still there.
Our compositor has kind of like two mode of operation. So if the buffers like align and everything like this, we have this concept of like a hardware display plane. So we can have the display controller like go and directly fetch pixels from those buffer. Or depending on like what's currently on the desktop, we may decide to just recompose the desktop because maybe we gave the plane to another. Maybe you're multi-mon and you're playing a video, and the video has a higher priority to get like the plane, for example, than your Linux app. So maybe the video will get like the display plane, and then the other app like will get like compose, depending on how many display plane you have on your hardware and things like that.
And did you want to talk about DRM buff versus not for sharing resources?
Yeah, for the DMA buff, like, so we've been chatting with folks about like whether we should try to go and implement like DMA buff or not. The main reason, so what we're trying to do is we're trying really hard to not to look just like a regular Linux. We don't want to go and do anything proprietary that basically like all of a sudden all software breaks and doesn't work correctly. So we want to try to get all the interface between application and the system, but just be standard. And only in framework and things like this, we need to go do things that kind of adapt because WSL is a little bit different, like because we're running inside a virtual machine, etc. We've looked at DMA buff in terms of like, hey, should we use DMA buff, for example, to share buffer between, say, Mesa and the Wayland compositor? The problem right now is the DMA buff is not completely standalone. So there's still, although you pass the DMA buff, both sides kind of know that these buffer were allocated with DRI, and basically you need to go and use DRI to figure out like what's actually those buffer, etc. So because our driver is not DRI based, those protocol already don't work out of the box. So because of that, we're looking at possibly just adding another protocol between, say, Mesa and the Wayland compositor to be able to pass buffer that are DevDXG friendly. And hopefully that should not impact application themselves. That should only be hidden like in frameworks like inside of Mesa and not leak outside. And for application themselves, it just look the same and hopefully work. But that's not a part we've implemented yet. Like right now, we kind of brought things up like on software rendering. And that's kind of what we're going to introduce first in our insider pool so that people can start using it soon. And then as people play with this and Jesse and team finish like the work on the layers, then we're going to work on merging all of this together so that basically we can have like GPU acceleration in with like the GUI app and zero copy and all that cool stuff.
Yeah, it sounds like the discussion, or not the discussion, the talk from James Jones later on, the buffer allocation talk and workshop should be of interest to you. Yep. On this topic. Very, very good. Well, that was it. So thanks a lot for this talk, and see you in 9 minutes.
Thank you.
Thank you.
Hi, my name is Natalie, and I'm here today to talk to you about the work that we've been doing using Mesa to build mapping layers. So this talk is going to focus on the 5 W's, the who, what, when, where, why, and how. So first off, who, basically all the people that have been involved in this project. I wanted to give a major thanks to all of the people who have helped. So from the Microsoft side, this has been mainly me and my coworker Bill. Our PM Angela has been helping out. And then we've been heavily helped by Collabora. So some specific names: Eric, Daniel, Gert, Louis Francis, Boris, and Ellie have been invaluable in trying to get this project up and running. So what am I actually talking about when I say mapping layers? What we have built is basically 2 API mapping layers, OpenGL on top of D312 and OpenCL on top of D312. So OpenGL on 12, as we call it, is basically a Gallium driver in Mesa. It looks very similar to Zinc, if you've heard of that. OpenCL on 12 is somewhat different. It doesn't necessarily leverage the OpenCL API implementation in Mesa, but it heavily leverages the compiler stack out of Mesa and expands on a bunch of work that's already been done there for the Clover OpenCL implementation. The runtime we are building separate from the Mesa codebase. We're basing it on top of our D312 translation layer, which is the core of our other D312 mapping layers. Specifically, we have a D311 on 12 and a D39 on 12 mapping layer that use it. So when? This project has been underway for roughly a year. Some of you may remember at last year's XDC there were some mentions of some Microsoft folks, and it wasn't really elaborated. We probably didn't talk to anybody. But this was the primary reason that we were at XDC last year, was kind of getting to know what the space is like, learning who's who in the Mesa community, and this was also our first face-to-face meeting with Collabora. So moving on to the where for this project. I'm not really going to talk about where in the world we were working on this. I think it's relatively obvious that the Microsoft folks have been in the Pacific Northwest of the USA. Collabora folks are hosted all around the world. Instead, I'm going to talk about where the source code has been, because that's kind of funny, actually. So at first, we started this project in secret. We had a private GitLab instance that was hosted by Collabora for us. Within the last maybe 7 months, we shifted to full open source. Eric from Collabora hosted a freedesktop.org GitLab fork of Mesa for us. And all of our development has been happening there ever since. And over the last several months, we've been working on upstreaming as many pieces as we can to the core mainline Mesa repository. And hopefully by the time that this talk is actually being given, we will have our D312 driver in mainline Mesa. So why? Why are we building mapping layers? Why are we building them in Mesa? There's a lot of whys to answer here. So I'm going to first talk about the Windows reasons that we're building this. The primary reason that we're building mapping layers for OpenGL and OpenCL is to support devices which don't have any Windows drivers for these APIs. We want OpenGL and OpenCL to work across our entire ecosystem, and unfortunately there exist devices that just don't have support today. So for example, Qualcomm doesn't currently provide OpenGL or OpenCL drivers. If you're running a device that has no GPU driver at all, you do get D3D support through our Warp Windows Advanced Rasterization Platform software driver. So if you're running in a virtual machine, for example, you have Warp, but it doesn't have an OpenGL or OpenCL implementation. If we have new devices that are coming online, it's a significant burden to write yet another API or driver implementation. So we're hoping that this can help accelerate the bring up of new devices. A secondary reason that we're building this is to enable our partners to eventually transition to using mapping layers instead of native drivers. This is obviously not a requirement, but from our perspective, it can potentially make things easier. It can reduce the development burden, the cost of supporting Windows, if you have one less driver to maintain. Another reason is interop. Being able to use a D3D device and be able to also issue GL or CL operations against it as well. That can potentially be relatively expensive. You have to create multiple devices, you have to use shared resources, you have to do shared synchronization objects. It's a lot to manage to make it work. We're hoping that by having mapping layers, we can provide an easier and simpler story for interop. And access to debugging tools. D312 has world-class debugging through PIX. There's also RenderDoc. Some tools out there do have support for OpenGL. Support for OpenCL is not great. But by being able to run an existing application through these mapping layers instead of a native driver, you can automatically get debugging support through other tools. So continuing on, we also want to support this for WSL, which we've talked a bunch about already today. One of the primary reasons that we want to support this for WSL is it means that we only need to provide one user mode driver from a given vendor in order to get a wide breadth of API implementations. And then why did we pick Mesa? When we were first starting this project, we were brainstorming how do we implement OpenGL, how do we implement OpenCL. When we were talking about OpenGL, it really doesn't make sense at this point to try and bring up a new OpenGL implementation from scratch. There are so many years of compatibility quirks and extensions and all kinds of things, and really, if we weren't using Mesa, this project just wouldn't have happened. This was the only viable approach to get an OpenGL driver. We weren't sure how we wanted to do OpenCL, so we talked to Collabora, and they suggested that we should use Mesa's compiler stack for OpenCL, and I'm definitely happy to say it was absolutely the right call to go that approach. It's been invaluable. So moving on to the how, which is the interesting part of the talk. What did we actually build? So what we've built consists of 4 primary components. First is a near to Dixel translator, where near is Mesa's intermediate language for shaders, and Dixel is D3D's intermediate language. Dixel stands for DirectX Intermediate Language. Very creative. Dixel is LLVM based. It's based on LLVM 3.7. So we built a custom LLVM bitcode emitter rather than using the LLVM codebase to do it for us. We built a Mesa Gallium driver, which is our D312 OpenGL driver. It implements the Gallium pipe interface and translates it to D312 API calls. And it's basically exactly the same thing that Zinc is doing for Vulkan. We built a D3D DXGI Windows WinSys, which enables us to use DXGI swap chains for present, which significantly improves efficiency and performance. And then we built a CLC to Dixel compiler, which goes through this crazy compilation pipeline from OpenCLC source through the Clang compiler to Spear, through the SpearV LLVM translator into the SpearV intermediate, through Mesa's SpearV parser into Mesa's near intermediate, through the near to Dixel path, and finally we get out Dixel at the end. So the near to Dixel converter, a few comments and details about it. Why didn't we use LLVM directly? Dixel is based on LLVM 3.7. We already wanted to have an LLVM version built into these components, but we didn't really want to stick with LLVM 3.7, which meant that we really couldn't use LLVM for both at the same time. They would conflict. The LLVM bitcode is unfortunately a very difficult thing to deal with. It uses all kinds of variable sized fields, and I'm not just talking about 8 versus 16-bit, I'm talking about 3-bit and 7-bit fields. Lots of unaligned data. It's kind of messy. And then on top of the regular constraints of the LLVM bitcode, we also have the Dixel validator, which makes sure that it is a particular layout. For example, metadata ordering needs to be in the right place. So what we built is basically a 2-pass approach. First, we translate the near into a bunch of data structures which match Dixel semantics, and then we do a pass over those data structures in order to emit the variable bitrate data. And then on top of that, the LLVM IR is actually wrapped up into another container, which has a bunch of additional chunks for things like runtime validation, so that D3D doesn't have to parse the IR directly. They can basically just pull out data and make sure quickly do validation against what's going on. The D312 Gallium driver, more or less self-contained. It deals with tracking state, allocating resources, managing command lists, all that kind of stuff. It has a lot of features that it needs to emulate, things that OpenGL requires that D3D doesn't necessarily implement. For example, wide points is something that has been deprecated since D3D 10. The concept of an interleaved depth stencil buffer doesn't exist in D3D12. Instead, D3D treats depth stencil as planar, where depth and stencil are completely separate. We were missing some vertex formats that OpenGL requires. For example, this RGB 10.10.10.2 format. GL has ability to support 8-bit index buffers. D3D only supports 16 and 32-bit. GL has the ability to do two-sided polygon rendering where the fill modes are actually different for both sides. So you can do, for example, wireframe on one side and solid filled on the other. I'm not sure exactly why you'd need to do this, but it's supported. So we had to emulate that. The concept of provoking vertex. D3D's provoking vertex is always the first vertex of a triangle. GL's is by default the last, but is actually configurable as well. So some emulation was needed there. The concept of combined images and samplers. D3D has completely separate ideas of a texture and the sampler that you're going to use to read it, where GL kind of conflates the two and treats them more or less as combined. So there was some work needed to separate those out. Point sampling of integer textures is actually kind of interesting, and this is one that we didn't foresee up front. But D3D only has the ability to do loads of integer textures as opposed to sampling. And specifically what that means is that if we want to do access with normalized coordinates, or if we wanted to get border behaviors, for example, clamp or a border color or repeat, we actually needed to write additional shader code to make that happen. Talking about the Windows system. So on Windows, Present is very complicated. If you're interested in specifics, I actually have a YouTube video that kind of covers what's available on Windows 10. There's a lot of options. So as a driver for OpenGL, we have access to a couple of callbacks from OpenGL 32. But unfortunately, they're not very useful for a mapping layer. You kind of really need to be a proper driver to be able to access them, which means that our only other option for getting contents onto screen was to use GDI, which is Windows' very old, the first iteration of graphics on Windows, which basically requires copying contents from your GPU render target into a CPU accessible surface and wait for the GPU to be done with that. And then you can copy that into another GDI surface, and then you can copy that into the window. And it is obviously very slow. That's a lot of copies, and there's a lot of synchronization overhead to make that happen. So DXGI allows an efficient queued present. You don't need to wait for it. You don't need to do a bunch of copies. But unfortunately, Mesa likes to be in control of the buffers that it uses for rendering, or the buffers that it uses to back the frame buffer. Where DXGI needs to be the one that actually allocates its own resources. So we were able to come up with a somewhat messy interface so that DXGI can allocate things and hand them off to Mesa. But it works, but it's not great. OpenCL. So as I mentioned earlier, the only thing that exists in Mesa today is the OpenCL compiler. The runtime is separate. So the OpenCL compiler is a very complex compilation pipeline. Fortunately, we didn't have to invent it entirely. Clover, which is Mesa's OpenCL runtime, did pioneer it for us. At the time that we started this project, Clover's support for OpenCL was kind of sub 1.0. It wasn't complete, and it definitely wasn't up to OpenCL 1.2, which is what we wanted to support. So we had a bunch of work ahead of us to kind of improve things. Part of that, there's a bunch of crazy conversions that you can do between floating point and integer values. You can do round to nearest even, round down, round up, and round towards 0 on every conversion from every possible type to any other possible type. There's support for work item offsets was missing, so CL has the ability to basically say this work item is going to start at a particular offset, and that just wasn't there. OpenCL doesn't technically require images, but all of the real-world applications that would want to use OpenCL for image processing, for example, would need image support, and that was not hooked up in the compiler, so there was a bunch of work needed for that. OpenCL requires implementing a very robust library of math functions, all the various trigonometric, sine, cosine, arcsine, hyperbolic, arcsine, all that kind of stuff. And it has very strict precision requirements for all of that. Fortunately, there exists an implementation available that we could leverage. It's called libclc, and it's inside of LLVM. So we did a bunch of work to enable our Mesa compiler to embed those implementations for us. Near had some pointer support available out of the box, but it definitely needed some more work to be able to support all the kinds of crazy things that OpenCL can do. And then we also had a bunch of Dixel-specific shortcomings to work around. So for example, Dixel does not have pointers at all, where OpenCL very much requires pointers. They're a core part of the way that you would write a kernel. So we were eventually able to figure out how to use the near lowering passes to be able to convert OpenCL pointers into a buffer index and offset, so that we can hand it to Dixel. And we have been contributing all of these things that we've been working on back towards upstream Mesa. And as a result, we've actually been helping to significantly accelerate Clover's progress for supporting all these features as well. So how will customers get their hands on this? Our current plan at this point is to ship as an app package in the Windows Store. So this is what the landing page for that's going to look like. In insider builds, as well as actually serviced into the stable release, we have updated the OpenGL and OpenCL ICD loaders. So when you try and actually initialize these APIs, they will actually check to see if this particular app is installed on your machine. And if they are, and if you don't have a native hardware driver available, we can actually go and pull these mapping layers out of this package and use them. And our current hope is in maybe a month or so's time that we can actually have a version of this live and available for end users to actually try out. And kind of proof of life, we're very happy that we have a bunch of apps actually working already. I don't have a live demo to show, but I do have at least a quick screenshot of Blender running OpenGL on 12. This is on a Qualcomm device, where not only was this app not GPU accelerated before, but this app didn't actually run at all. Attempting to run Blender on a Qualcomm device just failed because there was no GPU or no OpenGL support available. So yeah, it's alive. We've made a lot of progress. This has been a really fun project. I've been really happy working with the Mesa community, and I look forward to continuing to work with you guys as we move forward to adding new features, getting OpenGL 4.6, OpenCL 3.0, and getting WSL support as well. So thank you.
Okay, and now it's time for the questions.
Oh, there we go. Now you should be able to hear me.
Absolutely.
Okay. So I guess I can quickly go ahead and summarize discussions that happened while the video was playing. There was a quick question about using LLVM 3.7 for Dixel. Are there any plans to upgrade? Unfortunately, it's a little bit difficult to do that. D3D drivers are expecting to get LLVM bitcode that came from a 3.7 version of LLVM. So yeah, upgrading is something that is desirable. We could potentially do it in a new version of Dixel, like a shader model 6.7 or something. But unfortunately, the Dixel compiler is a fork of Clang as opposed to integrated into upstream Clang. So it's a pretty significant chunk of work to get a Dixel compiler on a new version of Clang. It's basically going to be reporting it and reforking it off of a new version. Let's see, was there anything else? It's just some comments and discussions about naming. That near stands for new IR, and Dixel is roughly as creative as that. And also, Jason mentioned that the DRM, DRI3 and DRI2 paths for Mesa's GL state tracker do have support for client allocated buffers. But yeah, at a high level, it's basically just the WGL Windows path that doesn't.
So if anyone has a question, it's about... Now is a very good time.
I guess while we're waiting for questions, I can go ahead and say that I forgot to call out a huge thanks to Jason Ekstrand and Carol Herbst, who have been instrumental in getting the OpenCL implementation up and running.
Okay, well, I guess that was, it was a very clear talk, so congratulations.
Thank you.
And I guess in 10 minutes we're going to be having Bas talking about profiling on AMD GPUs using tracing. Thanks a lot.
Cool. Thank you.
Bas, the stage is yours. Seems like we have some small problems with audio. Just give me a second so we can see what's going on. Can you say something? Okay, I think it might be on our side. It was working just seconds ago.
And now you can hear me. Great.
Yes, now we can hear you.
So, sorry all, I'm Bas. I'm mostly working on the RedV Vulkan driver for AMD devices. And today I'm going to talk about trace-based profiling on AMD GPUs. And we commonly use profiling to figure out what the most meaningful thing to optimize is and where there are any optimization opportunities. In my GL days, it was pretty common to record something with APA trace, and then on replay, we measure things like timestamps and GPU performance counters. And we typically did that per draw call. And the way that happened with API trace is you do kind of barrier, sample, draw, sample again, and barrier, and then take the difference between the two samples. However, that has a big issue with interdraw effects because everything is so isolated. And these days, GPUs are kind of like a pipeline with all kinds of shared resources. So there's a lot going on actually that you can't see. Of course, your first thing to do would be remove the barriers, but that has its own little problems. Like if you look at the left, like the typical way to do this is to sample at the top and the bottom of the pipeline, but otherwise just run in parallel. And then if we look at the right side, I just put some profile information there, like draw calls and then how long they took using that approach. And if we take like the fifth call from the bottom, like it takes 361 time units. But the question is like, is that slow? Is that fast? But it's waiting on the previous draw call to finish. And you really don't know. And it's really hard to figure out like what's the real expensive draw call among all of these, or maybe they're all expensive. And for that on AMD GPUs, we have something called thread traces. And the idea is that we can have the GPU dump to a buffer like all kinds of things. Like when a shader subgroup starts or stops, when a draw starts or stops, driver annotations, command buffer register writes, or other events like cache invalidations or barriers. And we over time have integrated this with the RedV driver. Like you can start an application and set an environment variable to a non-existing file. And then when you create the file, it deletes it again and traces the next frame and will give you a nice buffer on the TMP directory. And then we're going to visualize that. For that visualization, I will use an existing tool called the Radeon GPU Profiler made by AMD. Not to particularly tell you how nice of a tool it is, but to give you some ideas of like what kinds of interdraw effects are interesting to look at and can help you in your optimizations. And the big view from such a buffer is the wavefront subgroup view. So from left to right, you really have a timeline of your entire frame. And at the top, we look at the shader occupancy, like how many shaders are active in your shader units. 100% is good, 0% is bad, and in the middle is non-ideal, but it's not completely perfect because with 100%, like it includes SMT, so typically with 50%, it's all right-ish. At the bottom, we have all kinds of events, so all the light blue boxes here are draw calls, the red lines around the middles are barriers. And I'll give you a zoomed in version of how that looks like. And we can see here that draws are really a bunch of things combined. Like there's 2 boxes per draw with a line between them. And that's really like your geometry pipeline versus your fragment shaders. And then you also see some draw calls without a second box where apparently all the fragments are depth called or otherwise not needing a fragment shader. And zoomed in view to the top, like you can really see like bad places, good utilization, and you can actually split this out by things like draw call. So you can actually like, if you select this in one overview, see like, is there something that takes a ton of compute resources for a long time or something like that. And when we put these together again, like on the occupancy, we clearly can see in the middle of the graph that there's some utilization problem, like it's having almost 0% occupancy. And the big hint there is I selected one of the draw calls in the lower event view, and it pops up some information on the right about the draw, and the important thing is the text in red which says rolled. So it's about hardware context, which is really AMD's version of draw states. And yeah, if you change your state between draws, like we have to have multiple draw states in flight if we want to have multiple draws in flight. And it turns out we can have a maximum of 7 draw states in flight. And when you need another one for your next draw, but the other 7 are still busy, you're going to get a stall. So if we look at the event view, and I one by one selected them and see if there was a context draw, and then put a red dot in this image for where there's a draw state change, and you see like there's like a lot of draws that change state, and way more than 7. So there's a big limitation there in your throughput based on how often you can change your draw state, and not so much about being shader limited or anything like that. So this is really a limitation. And now you can figure out like how to avoid that. Like, should we spread these with more expensive draws, or should we avoid changing a state even though it's less optimal to avoid this bottleneck? So this has given you an opportunity to optimize. And another big optimization opportunity tends to be barriers. Like, for example, if you render to a render target and then want to read it from a shader, you of course have to wait till we finished rendering to the render target. The problem with that is that, like on a Vega 64, which it's kind of like you need 164K shader invocations at the same time to reach full occupancy, which is like a lot. And if you need to drain that, like that's pretty expensive. So there's basically 2 ways to help this. One, like it gives you a separate barrier view where you can go look like what are my most expensive barriers and stuff like that. And it gives you, I put some image of it below of a small set, and it gives you stuff like duration and drain time, but also like what am I waiting for? Like, am I waiting for a full GPU idle, or am I only waiting for compute shaders or vertex shaders or something like that? It tells you which caches to invalidate. Like if you take the render target versus sampling again, like you might need to flush some caches to make that visible to the texture units. And it also tells you like layout transitions that are not visible from the application. Like, am I going to decompress an image, compress it again, or do some other thing? It also tells you, it will also show you that in the timeline we saw earlier, and it will finally tell you what triggered it. And for drivers, it's very helpful that it also tells you why it triggered the barrier. And we can actually see that in the timeline view again, like the red lines are the barriers. So if you see like your occupancy goes way down and then there's a barrier, there's a good hint that the barrier might cause it. And then you can look at like, how can we avoid that barrier? How can we make that barrier less expensive? Like, can we batch things better? Or maybe a better layout transition will involve flushing less caches or less work for, say, a decompression. And of course, as an overall profile tool, RDP will provide you with all the necessary pipeline state to figure out like, why is this decompressing or not? And that's your second optimization opportunity here that it can really visualize and that you wouldn't see by just looking at individual draw calls. A typical trace for an AA game tends to be like a half to 1 gigabyte, and if you look at the GPU, like this is less than 10% bandwidth overhead, and it's a separate hardware block that it does this, so it's pretty low overhead. It's slower than timestamps without barriers, but it's faster than any of the replay tools, and typically your overall frame time will be pretty much the same as it is without the tracing. And finally, as a bonus, one of the events we can actually trace is executing instructions on a single chosen compute unit. So that's where we really can use this to look inside, say, a big compute shader to figure out like what parts of the shader are expensive. Maybe you can do something in the compiler. Maybe this is something for the app to optimize. And this is especially becoming more important as more and more games are using huge compute shaders as significant parts of their frames. Of course, not everything is perfect. Streaming performance counters are something that we can help with the occupancy problem, which is like occupancy isn't utilization. Like 50% occupancy will be if you don't need to hide latency enough to utilize all the hardware units. So ideally, you'd have something like, what's the utilization of my vector floating point ALUs? And for that, performance counters are just so much more useful. And streaming performance counters can like sample the performance counters in roughly each 100 to 200 nanoseconds. And it would be really cool if you could align that with your thread trace to figure out like, is this lack of occupancy actually causing a real performance problem here? Sadly, there's no RGP support, and RGP is not open source, so it's kind of hard to add it in to make this useful without writing something similar. So that's where we haven't quite gotten yet. And that was it. Thank you all. I hope I showed you some nice ideas for extra optimization. Are there any questions?
No, currently I don't see any questions on IRC, so I guess that would be it then. Unless something last minute will pop up. Nope. Okay, thank you very much for your talk. That was really good to see. And see you.
See you.
everyone. Good morning, good afternoon, good evening. Oh, we are around the world. I'm Ray from AMD. I'm Linux graphics team. I live in Shanghai right now, and it's a long time to see you since last XDC. And I'm very happy to see you again here, even with the online conference. At this moment, it's my great honor to have the opportunity to talk about the Linux software solution for the secret buffer object to all of you in the conference. And we designed the solution early this year. And in Linux, we have some specific use cases that is required secret buffer support. Okay, let's move to the agenda. Here is the agenda of this talk. I will introduce the background, trusted memory zone, and the supported platforms such as APU and discrete GPU. And we will introduce the secret buffer object and how does the kernel and the Mesa buffer do the handshake, secret policy, secret read and write operations. Above items are the dependencies and the conditions for the secret buffer solution. And after that, we will go to the implementation part, which has the IB protection mechanism and the secret command submissions on graphics, SDMA, and vSyn. And then discuss the display secret from buffer. After that, we want to show you the unit test for secret buffer from the libdian part and the related parameters on the kernel and Mesa, and the data comparison sample between the encryption and unencryption content. And finally, we will talk about the future working with the open source secret solution. Okay, let's go to the background. Firstly, memory encryption is a very popular topic recently. Most people would like to make sure their personal data cannot be accessed by any other guys, So we raised the memory encryption feature that protects the content cannot be accessed by unauthorized applications. So on Linux, we provided the secret buffers solution, which used the memory encryption for the content protection in our GPU platforms. We developed trusted memory zone to support video memory and system memory encryptions. Then Linux kernel and Mesa OpenGL and the user space applications are able to leverage the functionality of trusted memory zone to implement the secret buffer object for the protection on many user scenarios. Okay, move to the trusted memory zone. And what is the trusted memory zone? The trusted memory zone, we call it the TMZ, as well, is a method to protect the contents being written and read from memory. This memory presents both the system memory and the video memories. The new GPU support the full bandwidth ICE cipher. That's actually the hardware protection, which is much safer. So all the trusted write and trusted read should go through the S cipher before hitting the memory. And it's able to keep the raw memory data in safe under the cipher and cannot be accessed by the regular read and regular write. We use the TMZ bit in our GPU VM table and the trusted transactions state to provide multiple protection. Even if the TMZ bit is misconfigured. The content is still in safe and not exposure. So it's very safe at that time. And let's move to the hardware platform support. AMD has two kinds of GPU platforms that are the integrated GPU and the discrete GPU. And we also call integrated GPU is in the APU platforms and CPU and plus GPU. Right now, let's look at the difference for these solutions. In discrete GPU, only video memory is able to be encrypted. That's because the discrete GPU engine is unable to encrypt the system memory on unknown CPU platforms. So the trusted memory zone can only set up the video memory on discrete GPU platforms. However, the integrated GPU platforms, is actually the APU platform. In this kind of platforms, both the video memory and system memory are all able to be encrypted. Okay, let's go to the definition of the secret buffer object. AMD GPU supports 64-bit page table entry, and there are the page-based address, fragment, and the properties fields such as read, write, execute, and whether it is in system memory, and the cacheable and valid bit. We use one of them, bit3, as the secret property. Why the bit is set in page table entry? The page letter is pointed by this entry will be put into the trusted memory zone, and this can be encrypted. According this definition, AMD GPU kernel implements a buffer object-based protection. That is because the buffer object is the basic management unit in the Linux direct rendering infrastructure. All the memory operation is based on the buffer object, so we use the secret buffer as the unit as well. And all the TMZ bits should be set in the page table entries. If they are in the secret buffer, no matter what is system memory or video memory. Okay, let's move to the kernel. Kernel and Mesa secret buffer definitions and the handshake. And there are three user mode API that we introduced with this feature. The first one is the gem create encrypted. A kernel driver provides this flag and the gem create IO control. That's the BO level protection. And I mentioned before, and then libdm Mesa will use this flag for the secret buffer allocation. Mesa use allocate buffer to decide whether this buffer is secret or not, because the user mode is aware of which data they should be protected. If the gem create encryption flag is set by Mesa, and all the TMZ bits of the whole page table entries for this buffer must be set as well. And the second one is the IB flag secret. This flag is indicate to the indirect buffer is trusted or not, and Mesa uses this flag in IB handle of the command submission context to inform the kernel and whether the graphics engine needs to translate to the trusted state. And the third one is ID flags TMZ. That is very simple. And that's to indicate the TMZ capabilities is integrated or not on current platforms. and Mesa use this information flag to be aware of whether the current GPU support TMZ or not. Okay, let's move to the security policy. We have two kinds of blocks to need introduced. One is untrusted block. CPU as the untrusted block that is unable to decrypt the security buffer with the trusted memory zone. User cannot get raw data from CPU address, even the address is k-mapped with CPU page tables. And the other is the trusted hardware block. Owning the trusted hardware block has the capability to describe the secret buffer. All the encrypted memory is only able to decrypt the GPU page table mapping. We have any trusted hardware blocks such as the graphics, SDMA, VCN, and JPEG display engine. Let's move to the write operation modulation table. I describe the security write operation capabilities. The first column. The first column indicate the trusted transaction trusted state, and the second is actually the TMZ bit in the GPU table, and the third is moderation result that marks the trusted hardware block, whether it is trusted or not, and the last column is the encryption state in TMZ. And from this table, we can know only one of the TMZ bit in GPU page table and the transaction trusted state is on, and the data should be protected under the trusted memory zone, and that means if somebody mistaken to misconfigure the TMZ bit in the GPU table, the content in the buffer is still in the protected mode, so that's very safe. Okay, let's move to the read operation modulation table. It describes this format of the read operation table actually is similar with the write table. From table, we can only the moderation data its own, and the TMZ bit is set in the GPU table at the same time. Name the results can be decrypted, and the decrypted state in TMZ will be on. That means we have to comply all the trusted mode and the secret bit in the system, and then we will get the decrypt data on the protection mode. So, okay, let's go to the next page. For now, let's talk about the per IB protection mechanism. What is the IB? Let's say the indirect buffer. If you joined XDC last year, you may know the indirect buffer detailed, and if you want to know more information, you can listen to the recording of Let Talk in the YouTube. Okay, here the buffer, the IB is command buffer which stores the package, which the graphics queue is used. The kernel implements per IB protection to execute the command submission. And please look at this diagram. This is the graphics command ring. And we actually leverage the producer and consumer pattern to present the data structure. We have the GraphQL is consumer and the kernel is a producer. Once kernel produced a package writing to the command buffer, the write point will be increased 1, and we once the graphics queue consume a package from the command ring, and the read point will increase 1 as well, and they run in the same direction in this command ring. The IB is another indirect command buffer which embedded in the command ring, and the many operations package are actually in the IB. So firstly, let's look at the blue one, which is the legacy case. Once IB emitted, the kernel will inform the hardware into the non-trusted state. That means this IB will execute the regular read and write for data buffer in this IB. The data is not encrypted, so CPU is unable to write and read the raw data in this. The data is not encrypted in this buffer, so the CPU is able to read and write the raw data in this buffer. So that is the legacy case. If we let's look at the original one. It is the secret IB. Once this kind of IB emitted, the kernel will enforce hardware block translates to the trusted state. That means the IB will execute the TMZ read and TMZ write for secret data buffer, and this IB, the data will be encrypted and can be decrypted by the trusted hardware. And CPU is unable to read and write the encrypted buffer at that times. This is the operation for the command ring to handle the secret buffer case. Okay, let's move to the command submission with secret buffer on 3 different engines: graphics, SDMA, and VCN. The graphics use the from TMZ bit with the packet frame control package to control the graphics engine into the trusted state. Once the IB finished, the kernel needs to clear the frame TMZ bit to send the engine back to normal. SDMA as another trusted hardware block, which is to use the TMZ flag in the page table to decide to do the regular read and write or trusted read and write. Why the kernel used SDMA to do the secret buffer copy? The kernel needs to set the TMZ bit at OP code of copy linear package to let SDMA know it's doing the secret buffer copy. A VCN engine doesn't need the kernel support to switch trusted level during the context switch because it's able to switch by itself according to the TMZ flag in the page table. That will be smoother while we are doing the video playback on the secret buffer. Okay, let's talk the display engine. Display engine is different than the others. The secret state of display engine is based on the register setting. That means the display buffer only program a bit in the register to switch the secret state instead of using the TMZ bit of the page table. In this case, it allows the secret access to the secret buffer in VRAM without using page tables. As we know, this display buffer may use direct access for the local frame buffer. So at that time, there is no page tables for traditional TMZ flag setting. That's the reason we have to use the rigid setting here. Okay, we initialize the secret test suite in libdm and AMD GPU test. This test suite is to verify the secret buffer related functionalities in the kernel and with the user mode API from IO control. They are to verify the page tables, flags, graphics, and SDMA command submissions, and secret buffer migration. For now, they are still in progress on upstream. And please note, we use TMZ kernel parameters in AMD GPU kernel module and set AMD debug environment variables as TMZ to enable this feature. Okay, let's look at the data comparison. Firstly, this is the raw data pattern, dead beef, in the buffer. After it's encrypted, the data will be unknown and saved data. So that is reason. So that's very clear. The encryption data, and nobody can know what they are. These are the links for the kernel, libdm, and the Mesa changes for the secret buffer. You can refer the source code here. Finally, let's talk about the future work on this feature. Actually, recently, we would like to support wide one for AMD GPU platforms. So what is wide one? Wide one is the digital write measurement technology provider that's used by Chrome and Firefox, this kind of the web browsers. We would like to have the wide one digital write measurement solution both on the Linux and Android. And the secret buffer with trusted memory zone is the key functionality which is required by wide one. And both TMZ plus HDCP were leveraged by wide one to set up a safe channel for the digital million data owner on the AMD platform. We actually are working on the upstream of full end-to-end solutions right now. Okay, thank you. Any questions? And please leave the message and note here, and feel free to send me the email. And for now, I'm very appreciative to the X.Org Foundation to give us an opportunity to present the secret buffer here to all of you. I'm very happy, and thanks thanks to the X.Org Foundation very much. And see you next year. Thank you.
Trevor, the stage is yours.
Hi, and thank you everyone for joining. And I would like to give a special thank you to all the organizers of this year's XDC. I would imagine that planning a conference during normal circumstances would be exciting enough, but having to throw all that out and redo it halfway through is just phenomenal. I think they're doing a great job, and that's amazing. And thank you for accepting my talk as well. Today I'd like to talk about GSoC and EVoC, and specifically the X.Org's participation in that. My name is Trevor Woerner, and I have been the admin for X.Org's GSoC for the last 2 years. And prior to that, I also was a mentor for BeagleBoard's GSoC program. So I've done this a couple times, and so far I just wanted to give updates and make everyone aware of it. This is great, having the live audience, but also having this recorded and on YouTube, I hope will serve as a great resource for students in the future and mentors and stuff for people interested in what's going on with this program. This is not going to be a technical talk, so hopefully a bit of a break from all the amazing technical deep stuff that we've been doing so far today. But anyway, good time to check your email and whatnot, and just sort of go along for the ride. So what is GSoC? GSoC is a program that was started by Google in 2005. It's a program that is focused on bringing more student developers into open source software. I don't want to open a whole can of worms right now, but as we know, the kernel community, for example, is going through a lot of discussions right now on onboarding and the gap that exists between what a developer needs to know to be a developer and what a person would need to know in order to contribute to an open source project. And in my opinion, for example, universities and colleges do a good job of preparing developers, but there's always going to be a bit of a gap. Even a seasoned developer who's not worked with open source very much might find that a bit of a challenge. That there's things to learn in order to be a contributor to open source. And so this is a program that was started by Google. And what it is essentially is that open source organizations are allowed to post jobs, essentially. Students apply for and work on those jobs, and then Google pays them to do that. The program is a little bit North American. It's sort of geared more towards North American schedules. Students are in school from September and then write exams in December, and then from January till May or so. And then they're off for the latter part of May, and then June, July, and August. And they usually seek employment at that time, try to make a little bit of money in preparation for the next semester. And this gives them an opportunity to do something that would be very, very relevant. It also provides the open source community with people and opportunities to try and bring in more people into open source. Not everyone is fortunate enough to have professors that might be aware of open source and might be able to teach them about that. And so if they can find these opportunities, then hopefully we get excellent contributions to our projects, but also hopefully we get an open source developer for life, preferably. That's the ultimate goal. There's a website there that I've listed on my slides, and you can check that out. There's lots of information. You probably have lots of questions about who's eligible and what organizations and how to mentor and stuff like that. There's lots of FAQs on the site that will go through all that, and videos and documentation. And there's also a lot of stats too, which are pretty interesting. For example, GSoC 2020, this one that we just finished, there were over 50,000 students that had registered for GSoC to be part of this GSoC program. Of those, 6,600 actually submitted proposals, and there were 9,000 proposals that were submitted. Students are allowed to submit more than one proposal, for example. And of those 9,000 proposals that were submitted by 6,600 students, only about 1,200 were accepted. So it's a lot of work organizing all that, and Google does a fantastic job. It's not a huge subgroup within Google that manages that. And there were about 200 organizations that participated. Every year, the number of organizations about 200, and we were fortunate enough, X.Org that is, to have been one of those that were selected. So how it works, just digging in a little more under the covers a bit. The assumption is that you are a project that produces code, and that code has to be an open source or free software as per Google's definition of that. And the other thing too to get across is that this is Google Summer of Code. There's a coding component to this. It's expected that you're writing code for this. It can't be just, the contribution can't just be documentation. A couple years ago, Google started a season of docs to address documentation. So there is a separate program for documentation, but GSoC is a coding. We're looking to bring developers into the open source project. So the assumption is that you are an open source organization and that you have code that's released under a free or open source license. And around the January-February timeframe each year, organizations apply. I believe 600 applied this year, roughly. Anyway, so around January, February, the administrator, which would be, in my case, me, would apply, fill out the forms and whatnot to apply. And then around the end of February, Google announces the list of selected organizations. And then at that point, students start submitting their proposals. And students are free to come up with their own proposals if they wish, but they can also, every organization must have sort of a website where they list out proposals, suggested projects, which students can either apply directly for those, or that can be used as a springboard for their ideas if they want to have their own ideas of what to apply to. And then organizations then, the administrators and the mentors get together, go through all the proposals, and select those that they like. And that happens around the April timeframe. And then once that is done, then the organizations will then ask Google for slots, to be allocated slots. You'll say, we have these many great proposals. These ones are really strong. And so could we please have this number of slots? And then Google gets back to us and says, here are the number of slots you get. And they don't admit, I've never seen anywhere where they explain the correlation between how many you ask for and how many you get. If it's your first year as an organization participating, then I think the maximum you're allowed is 2. X.Org in the past has had up to 6, I think. But anyway, like I said, there were 1,200 proposals accepted this year for 200 organizations. So Google works through that and then gives you your slots. And then when you have your slots, then you then have to, if you didn't get all the slots you wanted, then the mentors and admins then have to go through and try and figure out which of the proposals they're going to then take. And then you offer that to the student. And as I said before, students can apply to more than one, or there could be many reasons why they might not accept your proposal, your slot. And the challenging part about that is if you have an unused slot, it can't be reused. You can't give it back to Google, unfortunately. And the belief is that there are penalties if you end up with unused slots. So it's a bit tricky. It's a bit of an anxious thing to try and figure out, get the slots right, hope the students accept, all that sort of thing. But anyway, it's part of the process. So that happens around April-ish or so. In May, there's a community bonding period. And it's an important time for students to get used to your organization. In our case, to get on IRC, to start interacting with the community, to start looking at the code from a high level, to start getting to know your mentor, to start doing meetings with them and sort of maybe do a blog post or something. And then in June, July, and August, that's where the coding is. There are usually 3 coding/evaluation sprints that occur in that time. And the mentor, so they'll code for 3 weeks, and then there's an evaluation period. The mentor evaluates the student, of course, and Google supplies the form, so you fill out the form. But the student also evaluates the org/mentor as well. So it's sort of a back and forth. And then at the end, around the start of September, by the time September rolls around, it's time for final evaluations. And then by the end of September, the results are announced. So organizations. So what do we do? So an organization needs an administrator, at least one, more than one preferably, and mentors. And I cannot stress this enough, the mentors are the cornerstone of GSoC. If there are no mentors, there's simply no GSoC. If we didn't have mentors, we wouldn't be able to participate. I don't have the technical chops in the projects that fall under the X.Org/free desktop umbrella to really be mentoring someone on the technical details. And so it really needs people involved in these. And the thing that I want to stress to the students, for example, at this point, is all the admins and mentors of all this project are volunteers. Google pays a stipend to the students, but the mentors and the admins don't receive anything for their time. And obviously, it's non-trivial to be helping someone work on a project and to be coordinating with an open source community. There's certainly commitments involved in that, time commitments, and a lot of work involved for them. And I can't thank them enough. It's absolutely phenomenal. So as I said, as part of the submission process that we do to Google, we have to provide a website that has our ideas. And Google's very explicit about this. You can't just simply point to a bug tracker and say, search for these bugs. You can't just simply tag bugs in your bug tracker and say, these are good GSoC projects. They want you to actually work on this, to actually have dedicated some thought and time to this. And so we do. This is the link here where we can go and look at the current summer of code ideas. And to the X.Org developers in the room, I would like to point out that this website could use a lot of work. There are a lot of older stuff, and I'm not sure if it could be cleaned up. If you are working in some subsystem and think you have sort of a side project that you don't have time for, that might make a really good 3-month project for a student, then certainly that would be fantastic if you would propose that. Ideally, it would be great if you would propose it and then volunteer to mentor for it. I mean, if you say that you're going to mentor for something, I'm not going to hold you to it. If things happen, if when next year's GSoC occurs, there are reasons that you're under time pressures and really can't, that's fine. So you can propose ideas and not volunteer to mentor for it, but it would certainly be great if you could do both. If you don't want to set up an account on that system, on the wiki system, just to edit the page, then just shoot me an email or ping me on IRC, and I'd be happy to look at the thing. So maybe when you're flying home from your virtual conference and you're stuck in your virtual 2-hour layover, if you could spend a minute or two just looking through that list and giving your thoughts, that would be really fantastic and really appreciate it. And it would be great to do that ongoing instead of me waiting till January and then sort of panicking and spamming all the email lists with, hey, please look at the list and help. So when you have a free moment, if you could look at that list, that would be fantastic. And so now a little bit for the students. For the students who want to apply to any of the projects on X.Org, you have to find a project, but more importantly, you have to find a mentor. There are a lot of students that kind of show up in our mailing list or IRC and say, hey, here I am, give me a project, and where's my mentor? And that's not the way that GSoC kind of works. We want to see students hitting the ground and going on IRC, being part of the community, looking for projects, and just involving themselves. Really a lot of get up and go type thing. In order for us to consider your proposal, we absolutely want to see you having already submitted at least one patch for review on any project. And it doesn't have to, it can be trivial, it can be a spelling change or something, or a formatting change. It doesn't even have to be accepted. Even, if you post it and no, we're not going to accept it, that's fine. We just don't want to be using up the GSoC time, the coding time, seeing if you have, if you know how to submit a patch, how to use Git and all that sort of stuff. So anyway, there's a contributing guide for students if you want to look at that. I myself, when proposals come in, I want to see a very concise proposal with detailed timelines and concrete deliverables. We get a lot of wishy-washy proposals that are sort of like, oh, I'll read the docs and maybe I'll see what needs to be done. I really want to see concrete, and I want to see week by week for the 3 months what you plan on doing. If you are accepted, you must be available for regular meetings. Time zones aside, we have to figure out, I personally want to see 2 meetings, meet with the students, whether it's on IRC or through some sort of online platform. It doesn't have to be video. I mean, it could be a video platform, but we just connect through audio, but I do want sort of to connect with you regularly. And we like to see blogs. We have a Planet, and which is a blog aggregator, and it would be nice to see students blogging about their progress and what they're working on. So statistics, how are things been going? So here's a chart that shows our participation over the last number of years. And 2005 and 2012, we weren't participating in GSoC, but you can see the orangey bars are the number of accepted proposals that we had, and then how many of those succeeded. So it comes and goes. And I have a spreadsheet that shows all of the students and stuff like that. And the total number of students over all the time that we've been doing this that we've ever had was 53. And of those, 43 have succeeded in their GSoC efforts, which is around an 81% success rate, which is phenomenal. That's code, that's features, that's stuff that X.Org / free desktop projects have. That is, that's been useful. Now, that's a good measure of success, but how many of those then go on to continue contributing? And by my estimations, about 19 or so of those students, which is about a 44% post-GSoC retention. Now, what I did was I looked at the student and when their GSoC ended, and whether there was any more patches. And in one case, one person contributed a patch like a year after their GSoC ended. So, that's not that's not a huge contribution, but it's still someone stuck around, to continue with the project. And what I don't know how to track is how many students, just because they might do an X.Org GSoC, maybe they become an open source contributor in another project. So I don't know how to track that. But for our project alone, that's a 44% post GSoC retention rate, which I think is phenomenal. So I have about a minute left. So now I want to talk about EVoC. EVoC is X.Org's version of GSoC. Sometimes we don't get accepted for GSoC, but sometimes we have a fantastic student that we want to bring in anyway. And so we have a little bit of funding ourselves where we can run an EVoC, which is basically our private version of GSoC. And so we can still do sort of a GSoC-y thing, but without Google's involvement. Most of this, it's mostly for cases where we don't get into GSoC and have a great proposal. And it's also a timing issue. So if GSoC's timeline doesn't work great for a student, then we can still bring them in. And that's the end of my presentation. Thank you very much. If you have any questions, I'll be in the QA IRC room. And yeah.
Okay, thank you very much. There weren't any questions, but there was acknowledgement that we've got Waypipe thanks to GSoC, and there was a mention that organizations also get $500 for each successful student.
Yes.
And there was acknowledgement that some stuff could definitely be cleaned up. And some people were hoping that we could get some students interested in Nouveau, so that would be nice to have. Yeah, that was a wonderful presentation. Thank you again, and see you around.
All right, thank you.
Melissa, the stage is yours.
I was this year GSoC student for X.Org Foundation. I am Linux kernel contributor, and now I am the newest VKMS maintainer. So in this summer, I worked to improve VKMS using IGT. VKMS is a software-only model of a KMS driver that enables a virtual display to test DRM and run X, and why not Wayland, in a headless machine. IGT is a set of tools to develop and verify the expected operation of DRM KMS drivers. And we can say that there is a mutualism between them, that improving one is fruitful to the other. So with this in mind, my primary goal was to deliver a fully working and bug-free subset of GPU tests. That was the KMS cursor CRC. To get a set of to get a sense of the amount of work, I started by checking the status of this test for VKMS. However, things didn't start so well here. The sequential execution was unstable. I mean, the unique run of a subtest was passing, but it failed when in the subtest sequence. This behavior caused confusion, annoyance, and a lack of confidence for both the VKMS and the test suite. At a time, I could only classify the issues. So we have tests skipped for not meeting requirements. This mentioned a cross-cutting issue in sequential execution that I call mood swing, and fixes. Test case that fail in any context. So VKMS did not meet some test requirements. The first was the cursor size that should be larger than the standard 64 by 64. And after some reading, I realized that I did not to invent the wheel, and VKMS software only. So setting the max width and height of the cursor in the mode configuration control structure was enough to increase the test coverage. With this solved, it's still missing non-square cursor size. However, I think it looks very specific for Intel drivers. And if I confirm it, I think it's better to move this part of the code to the Intel test suite. And the last missing requirement will only be met when the VKMS support more than one CRTC. And that is a little more complex work to do. So the biggest challenge of my project was the instability of sequential subtest execution. I started with the following information. I have inconsistent results between a unique execution and a sequential one due to a timeout failure while waiting for the first CRC. And the first failure triggered all the others. So initially, I suspected the test itself. I'm not sure if it is a good way to start, but okay. And yes, it has an issue. When a failure happened, the test skipped the cleanup step. I had some progress, but was not enough. The situation just evolved from sequential failures to alternated failures. I thought there was a mismatch between VBlanks interruptions and the CRC captures. So I decided to set the pace, and the test should wait for VBlank before start the job. I thought it was necessary. And the second change seemed to work. While waiting for feedback, I shifted to the real failures. But it was not so real. The DPMS subtest was failing, but there is a commit in the past that reporting that it was working. So when did the situation change? Examining the Git history, I found the change, but it was correct. And in addition, I received feedback of Eric and Eric Hiler and Daniel Vetter, and thanks guys. And I realized my second change on KMS cursor CRC was not effective, and the IGT was not built here. So, well, time to ask the community for help, but how to start? IRC was still scary to me, so I tried the mailing list, and I found 2 people discussing a similar problem, Daniel and Sidon, and without invitation, I joined the thread, and a long, very long debugging process started. I can say no, it was not just debugging. It was amazing code debugging work. And during this process, I could also explore basic tools like ftrace, dmask, ctask, and key workflow. We did some wrong attempts, but thanks to Daniel's guidance, we found the most effective solution. That was to ensure VBlanks happens while the composer work and CRC capture is needed. In this path, solve almost everything, stabilize the test execution, recover the DPMS subtest, and the suspend test case is successful now. I also learned a lot with this co-working, and I felt now more comfortable talking to the community. So finally, the last failure, it was an old friend, my old friend. Initially, it just looked like a bug fix, but the fix just changed the situation from failure to warning. And the effective solution was to implement a to-do, a method to-do that is alpha blending. And that was what I did. And the last subtest was solved. But too good to be true, I decided to ask for trouble. And I changed the original transparent case to a kind of translucent cursor to test non-extreme alpha values. And this translucent case failed. I examined pixels, each pixel several times to figure out that IGT and DRM consider pre-multiplied alpha. And the funniest thing is that this information is already documented. I updated the formula and also refactored the alpha test to include more alpha values. And then I sent each path to its Dewey project. Conclusion. Well, after this summer, VKMS passed in more test case of KMS cursor CRC we could increase the task coverage and without failures or instabilities, and also got a new feature, the alpha blending of plans. Besides, I also could contribute to add write back to VKMS and KMS write back to IGT. Both was made by Rodrigo. And I reviewed some VKMS patches and also sent some improvements to key workflow. That is a set of scripts that helped me a lot in my development task. And so what is next? First, I am the newest VKMS maintainer, and I think I have a lot of work to do. I want to finish the implementation of overlay plan, and Rodrigo and I plan to check some ideas for implementing a CI for VKMS. So I would like to thank Rodrigo, Trevor, X.Org, and DRI community.
So far, nothing. And apparently, okay, there was a small hiccup with the stream, but it's back. Well, while waiting for some questions, I just want to say congratulations for managing to become already a maintainer in the kernel. This is something that is pretty rare.
Thank you.
Okay, and Daniel Stone is asking, did you already look at any CI solution like kernel CI or GitLab CI?
Yes, I did, and I think we could have some ideas from that to use IGT and this other solution for VKMS.
Okay. Well, I guess that's it. We don't have any other question. So thank you very much, Melissa.
Thank you.
And
yes, this is my contact. The way if anyone can contact me is in the screen. So So bye.
Bye-bye. Thank you. And the next talk is going to be from James Jones and Simon Sir in 16 minutes.
Okay, so I guess it's about time to start. We'll see if James is actually online, but we had some technical difficulties. So we have quite a few people here. So we have Simon, we have Daniel, we have John, we have Laurent, we have Jason, we have Alex, and we have James, who's going to present. And the stage is yours, folks.
Okay, so it seems like James is trying to join again.
Yeah, when I present, it starts freezing. Of course, only now. Still there?
Yeah,
yep, we can see it now.
We'll see how long that lasts. Okay. Welcome to the XDC 2020 version of the Allocation Constraints talk. I'm James Jones. I work at NVIDIA on the Linux graphics driver. I've been working on Unix device memory allocation problems for several years now.
Yeah, hi, I'm Simon Sir. Oh no, James just disconnected, it seems. Oh, was it the old James? Oh, okay, never mind. Okay, so I'm Simon Sir. I've been working on Wayland for quite some time. I'm working at SourceRoot, and I'm pretty interested in fixing the allocation constraint issues. So I've been working with James for this this year's edition. Yeah. So let's first begin with describing what we are trying which problem we are trying to solve. So hardware can do everything with any buffer. So there are some hardware limitations that make it so you can't just allocate any buffer and use it for anything. For if you want to display a buffer, there are some restrictions. If you want to render to a buffer with a GPU, there are some restrictions. So all of these hardware limitations depend how the hardware is used. So the set of limitations to display something in any NVIDIA GPU will be different from the set of restrictions that the buffer must satisfy to render something. Historically, the driver have been accounting for this internally. Nowadays, a lot of setups have multiple devices involved. There are multiple examples of this. For instance, you have SoCs with split display and render engines. There are also some laptops with integrated GPUs and discrete GPUs that you want to share buffer between them. You may want to do a bunch of stuff like displaying, rendering, using video hardware acceleration, and with the decoded videos, for instance, process them in the GPU and then display them. So all kinds of things. So the problem is basically we have multiple drivers. Each driver is not aware of other devices' limitations. How do we make everyone agree? How do we allocate a buffer that can be used on multiple drivers at the same time?
Okay, let's start off by going through some definitions of the terms we're going to discuss in this presentation. The most basic one is a constraint, which is a single atomic definition of one limitation of a device or engine that's trying to access memory in some way. So examples of a constraint would be any kind of address or pitch alignment requirements, a maximum buffer size or pitch, locality, like if memory has to be allocated on a chip that's physically near to the device in question or actually on the device. Contiguity, meaning the device can't access something like a scatter-gather list. It doesn't have virtual memory capabilities. It has to operate only on contiguous pages. And then some kind of baked placement or interleaving, where you might need individual pages, bytes, or even bits to be placed in individual banks to get the required performance or the required properties. Constraints are atomic and self-contained. That is, the individual constraints don't rely on other constraints to be fully expressed. They stand alone, and you can operate on them independently of each other. And constraints can be mergeable. So if you have something like a pitch alignment requirement, and you have two different ones, you have, say, a pitch alignment of 4 bytes and pitch alignment of 6 bytes. If you merge those, you take the least common multiple and get a pitch alignment of 12 bytes, which covers both use cases. Usage. Usage is a description of what operations are going to be performed on the memory for a given engine or device. So some examples of usage are a pixel format or a textile format, operations like texturing or rendering, video encoding, decoding, or capture are using a display, for example, displaying at one particular resolution and at a particular rotation setting. And the granularity at which you express these might vary depending on which API or driver or mechanism you're using, but to some degree you'll have to propose some usage for the device so it can report to you constraints. A constraint set is a list of individual constraints imposed on memory for a given usage. So for any given usage you propose, a device has to be able to report to you all the constraints that apply for that device for that usage. And so we call that a constraint set. Like constraints, constraint sets can be merged. And the most useful property of that merging is that when you merge multiple sets, you get something that describes the constraints that apply to the union of all the usages that you specified when querying those sets. So if you asked a display device what its constraints were, and a rendering device what its constraints were, and then you merge those, the result would be something that expresses all constraints that apply to both displaying and rendering. Another property that's useful is that when you merge constraint sets, it does not in itself produce new constraints. So if you have constraint set A and constraint set B, and you merge both of those, the resulting set won't be any longer than the length of those first two sets combined. And right here is a small example illustrating what a merge operation applied to a constraint set looks like. So you see there's a simple constraint set that only has one constraint, a surface alignment requirement. Then there's a second constraint set that has both pitch alignment and surface alignment requirements. When you merge those, you take constraints of the same type and merge them individually, producing one new constraint. And if there are constraints that exist only in one list, you just concatenate them to the new list. So you see the result there in the diagram.
Yeah, so this year's edition is a little bit different from the previous editions in multiple ways because the landscape has changed a little, modifiers have happened. So this proposal strives to integrate with the existing ecosystem. That means integrate with APIs such as OpenGL, Vulkan, KMS, GBM, video for Linux, maybe VA API, and so on and so forth. We designed our proposal to be extensible so that we can have a proposal of just a minimum viable product, and then extend the proposal as we go. And if a new driver comes in with new hardware with different requirements, we can just add new features to the mechanism and extend it like this. We focused only on constraint resolution alone, so different but related problems such as trying to pick which allocator to use, we haven't addressed these issues. Other issues like I/O, MMU, discovery, or programming are not addressed. It's already a big task to do only constraint resolution.
Definitely. So trying to address those design goals, start out with a high-level design proposal, then drill down from there, sort of talking about how we came up with the design we did, and then how we got to a low-level proposal at the end. So at a high level, like we said, we wanted to leverage existing APIs. So we use the existing API mechanisms to describe usage. So that means things like Vulkan image properties for image creation, the existing like EGL image mechanisms where you specify a DRM format or other OpenGL texture format parameters, and DRM KMS planes for display, specifically planes, and then how also all the parameters you specify at mode set time as well. You query constraints from an existing API given a piece of usage or a description of the usage you want to use. So this is similar to how format modifiers are queried now. And then the one difference there is that constraints are reported separately for every given layout that you use or every given format modifier. So if you queried 5 format modifiers already after specifying your usage, then you have to, for each of those format modifiers, again query a constraint set. So you end up with this kind of combinatorial level of data. So there is a lot of data here for the application to manage. We'll provide logic to merge constraint sets in some common code. This is the main operation you need to perform, but it's the same for any component using this mechanism. So hopefully we don't have to write it more than once. And after you've merged your constraint sets from all your different devices and usage, you can pass them on down to an allocation API of your choice at allocation time. And it shouldn't really matter which allocator you use, as long as you pass in the right constraints, it should be able to give you compatible memory of the same type.
Yeah, so here's an example of how that would work in practice. So if you're, for instance, a compositor and want to render to a buffer and after display it on screen, you could query display constraints from KMS and then render constraints from OpenGL. Then you can take both of these constraint sets and merge them together, and you obtain a constraint set that is suitable for both. And you can, for instance, pass the merge constraint set to GBM to allocate a suitable buffer. So yeah, just a little more detailed example with some explicit constraint sets. If KMS says, I want buffers allocated in local video memory aligned to 1K, and OpenGL says, I want buffers aligned to 2K, then you can allocate with GBM buffers that are in local video memory and aligned to 2K, and both KMS and OpenGL will be happy.
Okay, so given that high-level design sort of as an initial goal, we worked through a bunch of case studies to build up our detailed requirements and to evolve the design, see if it held up under stress. So this first case study is the simplest case, more or less, that we started out with as sort of a base case. This is the problem of satisfying pitch alignment requirements for various devices. So people have probably seen bugs like this in the wild, where if you're doing something like prime render offload, you have multiple GPUs involved, and they might have different ideas of what the stride or pitch of the buffer that you're presenting should be. I have some examples here of some pitch alignment requirements from various vendors that we tried to dig up. Please take these with a grain of salt, because these were dug up at the last minute, and they're mostly for illustrative purposes. On NVIDIA hardware, I know that we have 32-byte alignment requirements for pitch if we're doing rendering or texturing, and 256-byte alignment if we're going to do display. AMD for display seems to require 256 bytes in practice. On Intel, it seems to have various cases. It can be as low as no alignment requirement or 1 byte alignment for some use cases, aligned to the bytes per pixel for other operations, and then it seems to be 64-byte alignment for display. So if you want to, for example, render on an NVIDIA GPU and display on an Intel GPU, you have to agree on what the pitch is going to be. And then if you want to do texturing as well, like if you're in the typical use case of some kind of system compositor, you want to make sure all these operations work on some combination of those GPUs. So what you would do here is query a list of modifiers for each device, specifying the usage that you want to have available, and then intersect those modifiers. And this ends up being sort of trivial here because the only modifier you're going to get that works with all of these is going to be linear. Then for that linear modifier, you would need to query and merge the constraint sets from each API that you're using again. And again, at this step, you have to specify the usage over again. Because the modifier is derived from usage, but does not imply usage itself. There's a many-to-many relationship there. So the constraint set query and stuff needs to know what your usage is as well to be able to report the correct constraints. And then, as we saw earlier, merging for this type of constraint is relatively trivial. You just find the least common multiple of all the pitch alignment requirements and report that as the overall requirement.
We have a small question on IRC. It is unclear who does the merge call. Does it have to be the client allocating the buffer? Can it not be handled inside GBM, similar to Graalloc?
It can be any component can do a merge. The result should be the same. If you pass in 3 different sets to the allocator and have them merge them, that's fine. But I think it makes the API easier if you only have to pass in 1 set across every API boundary. So I think anytime you have 2 sets available, you should probably merge them down to 1 and pass them around. But that doesn't really affect the design. I think it works either way. So a couple lessons from the first case study. This type of operation is applicable to any kind of minimum alignment requirement. So surface alignment, pitch alignment, width or height alignment requirements, anything like that. The same basic thing also generalizes to minimums and maximums just by replacing the merge operations with min and max. And it's also relatively simple to code up and visualize. I think most people understand how this works and the problem it solves. So it's a good example to start with, I think.
Okay. Another use case is local video memory. So some hardware like discrete NVIDIA display engines, they can only scan out from local video memory. So if you want to display something, you need to add this constraint. The naive solution will be to add the very simple constraint which just says, I want local video memory without any value. So there are a few problems with that. First problem is local to what? Because if you have 2 devices, a simple constraint that just says, I want the buffer to be local, it doesn't describe which local to which device. The second issue is that some devices have multiple local heaps. So if you say local, maybe the driver needs more maybe the driver needs more granularity to know exactly where to allocate. So our solution is to add a new constraint, which is a heap constraint. And inside the heap constraint, you have a list of possible heap IDs. So the driver can say, I want the buffer to be allocated in heap A or heap B, and that's a constraint. So each device can expose multiple heap IDs. So GPU can have a local video memory and another type of local memory. We can namespace heap IDs by subsystem to prevent conflicts. For instance, we could have a namespace for DRM above heaps, another one for DRM. And merging 2 constraints, heap constraints, is just taking the intersection of the heap IDs. Yeah, so that works for both input constraint sets.
I mean, I guess what about the case of if you have like multiple sort of attributes on a heap, like if you have the ability to access system memory, but you might have a constraint that a particular engine needs to needs to scan out from uncached memory as opposed to cached.
Yeah.
I mean, I guess we could just make that up as a separate heap, but
yeah. So yeah, it's still an open question. There are a lot of open questions in our proposal, and I think part of what you're saying is the second point in this slide. Maybe we need some kind of regular or shareable memory heap, or in general heaps that are universally recognized. And maybe we need to be careful about combinatorial explosion if you have a lot of flags. Maybe maybe we can come up with other constraints. Maybe not. Yeah, we need to discuss about this.
Yeah, I think a lot of that was
just
there was a talk about how to decide what is a heap and what isn't. I think at Linux Plumbers conference this year. And there's a lot of those questions, like, should the attributes be part of the heap? Should they be a separate theme? That separate theme might be another constraint that says I cannot do cache memory, for example. It's not really clear yet, but the idea of a heap ID seems like it's powerful, at least. So that's the starting point for our proposal.
If the heap ID is generic enough, it probably can work. The way that this is done in Vulkan is sort of a two-tier system. There's heaps and then there's types. And there's a mapping from types to heaps. And the types contain both the heap and properties like is it cached, etc. And so if you kind of map Vulkan types to these heaps, then it should be able to describe what you need by kind of baking it in. It does mean that you can no longer, for instance, figure out how much memory has been allocated from a given heap, because there might be some overlap in terms of the underlying allocations. But I don't see why we couldn't sort of bake that kind of information into the heap ID, as long as it's a driver controllable thing in some sense.
Yeah, and in some ways this is the generalization of the Vulkan mechanism to cross-device.
Yeah. So lots of things to still be discussed. Another thing we can see about this is that merging two constraint sets can fail because one device may say, I want local video memory to my device, and another device may want to say, I want local video memory for me, and then it doesn't work if we intersect both of them. But this makes sense because you cannot scan out from both at the same time. But yeah, just something to keep in mind. And yeah, we need to come up with a good heap ID mechanism. I think the discussion just right now is a good demonstration of this.
Another difficult problem we ran into was what to do with unknown constraints. So these happen by, as a property of the system we've defined. We have a design that disperses the constraint knowledge throughout the system components that you're using. So you're going to have a lot of system components talking together, and it's not realistic to have all of them version locked. At the most simple example, you have maybe an old kernel in the user space, or vice versa. But you might also have a mixture of Mesa drivers and proprietary drivers. You might have a mixture of old system compositors, like an old Wayland compositor, and a new application. Hopefully they're at least using the same version of the driver underneath, but they might not be. So at some point, you're going to have a component that will encounter a constraint that it's not aware of. And then the question is, what do you do then? So assuming you're the component that sees an unknown constraint, you can either ignore it, in which case you might still succeed allocation, but you might get something that's not actually compatible with the usage that was specified because you haven't accounted for all the constraints reported. That seems not great. The other option is to fail the merge or allocation. And this seems like it provides more robust behavior at first, but it can also fail in this corner case where you have these things that we refer to as implicit constraints that later become explicit. So let's walk through that in more detail here. Too far. So in this example, we have an implicit constraint of local video memory. So let's say in the current status quo, drivers use some kind of logic to place certain allocations in their device local video memory. It might be like when you think this might be something that's going to scan out, it ends up being placed in video memory implicitly. Then at some point, someone comes up with this design that says we should make a constraint for that. Let's make it explicitly specified by the usage, whether or not you need to be in video memory. And so this is great. You update your allocator, you update your components that specify usage, so they all are aware of this explicit constraint. So now you only have memory placed in the device local video memory when you actually have a constraint saying that it needs to be placed there. The problem is that if you have an old allocator, or sorry, an old component reporting constraints, so it's not aware of this constraint and doesn't report it, mixed with an allocator that has been updated to use the new explicit constraint and hence won't place memory in device local memory unless it receives the constraint, you're going to have a bug. You're going to get memory that's not placed in the required memory location because the constraint wasn't specified. So that's probably bad. That means you're going to have, in the standard bug of new kernel regressing old user space probably.
I think what we learned from modifiers, obviously everything else worked perfectly well and there were no problems. But it's got to be do it with every single component, explicitly opting in or not at all and just go back to the old implicit world. So I'd say in that case, if you are moving to an explicit constraint on placement, then maybe you need to have everyone communicate down that the placement can be universal or don't care or whatever, rather than trying to mix the two worlds.
Yeah, so that's what we came up with. We couldn't have something so granular as requiring you to opt in or out of constraints in general, because then you could never introduce a new constraint to the system. But yeah, rather than doing it on the granular basis of every single individual constraint, we've opted to propose that you have a versioning system for the constraints themselves. So for every different constraint that's introduced, it will have some implicitly associated version, which is basically an incrementing number in the file, the header that defines all the constraints, that is incremented whenever we have a new release or whenever a new one is added or something along those lines. So each version has each constraint has an implicit version. Additionally, to make sure everyone's on the same page, each constraint set contains a required special case constraint that reports the version of that constraint set. So anything that reports constraints, we'll set that to its last known version, the version that it's aware of and using. And then when you merge constraint sets, the merge op for that type of constraint is take the minimum. Additionally, allocators and really anything else that operates on a constraint set, so this includes the merge library, the common merge code, will merge in their version when they perform that operation on the constraint set. And then the onus here is on the allocators to preserve their prior implicit constraints, basically what Daniel said, fall back to default behavior. If they see a constraint set that is less than the version of the explicit constraint that they're operating on. So if the allocator was updated to handle explicit requests for video memory and it saw that the constraint set was less than the version that added that constraint, then it would fall back to its old behavior and use heuristics or place everything in video memory. And once you have this, we reasoned out that you should be able to safely ignore constraints that you're not aware of, because it should result in, if everyone's following the rules, it should result in behavior no worse than before the constraint was introduced. In that you'll fall back to the heuristics or whatever it is. It might not be good behavior, but it won't be any worse than before. There won't be regressions.
So there's a question from IRC, quoting, if I understand correctly, to produce a list of acceptable heap IDs, you need to query the heaps that exist, right?
Potentially. If you don't somehow know them, yeah. There's a lot of, I'll probably save those questions for the workshop. There's going to be a lot of questions about heap IDs. I think, as I said, heap IDs is a large problem in and of itself. Back to the current case study here. The lessons we learned from this were that both backwards and forwards compatibility are important. If you don't have one, you really don't have either. And ignoring unknown constraints, as I said, should produce behavior no worse than using an older version of the component that was expressed in that constraint. So if you don't handle a given constraint, if you just ignore it, it should be no worse than if you hadn't upgraded whatever piece is reporting it.
Yeah, so we've now seen all of the high-level stuff. So we can maybe dive into the lower-level design proposal. Yeah, of course, all of this is subject to discussion, and the more low-level you get, the more you can get into bike shedding territory pretty quickly. So nothing's final. We can discuss. So in our proposal, constraint sets are variable length lists of 64-bit integers. The first list item is a header with a type and a size specified. So you have basically the header and then a certain number of items depending on the size, and then another header, and so on and so forth. The explicit length is necessary to skip a non-constraints, which is we want to do that with the versioning scheme we've seen just before. In our design, most constraints are vendor agnostic. Yeah, we've tried to come up with a solution which doesn't involve vendor-specific constraints, but maybe those are required somehow. This will complicate merging a little because we can't. It will be difficult to have a single merging function. Something that would further complicate the design will be to have fully opaque constraints. Yeah, we'll see. But the current proposal is to only have generic constraints. So we've implemented the merging logic and some helper functions in a sort of shared library. It's pretty small, but it needs a home, and it needs to be shared between the kernel and user space. Because both will use it. So the current proposal is to use a header-only library in kernel UAPI headers. Maybe it's not the best solution, but at least it's the simplest solution. We can discuss that later. We have no helpers to choose which allocator to use when doing the actual allocation. So we just recommend user space to guess and check, to just try, basically. So user space is already aware of all the DRM devices involved in the constraint negotiation. So user space can just try and issue them until it works, basically.
So there's another question from IRC. Could the constraint version be simply the maximum known enum value?
The maximum known enum value?
Enum value, yeah.
I assume that means the maximum known type, if it's a...
Yeah, I mean, that sounds possible, yeah. It seems like the possible device, possible solution, because yeah, each time you add a new constraint, it increases the version, so that could be it, yeah.
And I think that's very similar to what Simon wrote up actually in the example code too, which I'll get to later.
Yeah, I just wrote it manually, I think, but yeah, right, I think the latest constraint number was the version number as well, so. Yeah, so here's an example of how this could work in EGL, for instance. So you'd use EGL to query rendering constraints, and so rendering is a little bit, yeah, rendering and texturing. So we've introduced a new entry point, EGL query DMABUF constraints X, which will take a format, a modifier, and an external only flag, which is also used in the modifiers extension. Basically, more or less says whether it's for rendering or texturing. It's a little complicated than that, but with all of these inputs, the entry point could output a constraint set for this usage.
Like usual for Vulkan, it's a little more complicated there. The one line of code becomes several. The current thought is to extend VK get physical device image format properties to return constraints in addition to the other information it returns. It's not completely clear yet how that squares with the usage of that same function to report format modifiers. I think you might need to specify only one modifier per call and call it multiple times or something. That's not totally worked out yet. But basically, you get a constraint set out of usage you specified using that function, since it pretty much exactly specifies how you're going to create a Vulkan image. Additionally, we would have to extend the VK memory allocate info structure so you can allocate memory with a set of constraints applied to it. So that this struct is just another input struct to memory allocation that specifies all the constraints you want to use. We would also have to extend image creation. And one of the main reasons we have to do that is if you have something like that pitch alignment constraint we were talking about earlier, it's obviously going to affect the layout of the image, not just the type of memory allocated for it. So in order for the Vulkan implementation to be able to report memory requirements for like a pitch linear image properly, it's going to have to know what the pitch alignment requirements are. So they have to be passed in an image creation time too. And we thought about doing this the other way around, where you just get constraint sets out of get memory requirements, or whatever that function is called. But then you have that chicken and egg problem where you create an image first, and then what's the pitch of that image, and then it reports the constraints, and those constraints might affect the image layout, and you're going in circles there. So that probably won't work that way around.
So another question from IRC. Isn't it a bit clunky to expect user space to just guess and try multiple times? Isn't it possible to give it something that's known to be good?
So that's for the which device to allocate from, right? Yeah, I think the question is user space needs to guess the device where allocations must be made. Yeah, so it's a difficult question, and yeah, maybe we can come up with something, but we've not focused on solving this issue, and we've just said, yeah, let's fix everything else, and maybe then we can think about fixing this particular issue. And if you have something to add, James.
We haven't deferred it just because it's hard either. It seems like a lot of stuff is in flux here. Like it seems like there might be designs evolving in the kernel that might give us more options very soon, or it might be that the current designs are all we have. It also might be the case that constraints can themselves express the device that is required for allocation. It's not totally clear if that's a good design or not yet. So there's a lot of options here, and I think the problem sets don't necessarily intersect that much. I don't think solving that precludes solving the constraint problem.
All right.
Yeah.
Okay. Oh, are you going to say something, Jason?
Yeah. So one of the problems that kind of gets into this mess when it comes to specifying heaps as constraints and dealing with allocation on different specific GPUs, we have some hardware where there are modifiers that basically imply that it has to live on exactly that GPU, but other modifiers might allow it to be in system memory. And so if you're sitting in a multi-GPU setup, there may need to be some sort of a mechanism for saying, if you use this particular modifier, then you have to be on dev DOI code 1, and it has to be local memory there.
Okay, so that's
an example of the type of thing that we like.
Yeah, that's also come up with logic, to be fair. Unfortunately, the only thing harder than naming and identifying heaps seems to be naming and identifying devices. So I don't have any good suggestions, to be honest. But at least you're not the only ones.
Yeah, that's kind of why it was changed. I think in my older proposal it was device IDs instead, and now it's heap IDs because they, even though they're hard, they seem less hard. But yeah, maybe you can constrain that by saying you have to use that particular heap on that device, and that's just a proxy for that. But you could also have device IDs.
Yeah, depending on how heaps get advertised, if you're allowed to have heaps in the global list of all heaps that exist, that are implicitly tied to a particular device, then it probably can be specified simply as a heap constraint.
Yeah.
It kind of depends on what heap ID ends up meaning in the long
run. I think that has to be true anyway, because there'll definitely be some kind of heaps which are unavailable to some kind of devices. If you have, say, a heap which is non-bar exposed, then that's not going to be useful for other devices. So I do like that idea of solving it with the heap ID and then tying particular heaps to device access.
Okay, we're getting short on time, so let's try to get through the rest of the slides here.
Okay. So yeah, let's talk about KMS. So to query display constraints, the natural solution is to ask KMS. So KMS is a little bit complicated because usage is kind of hard to describe. For instance, if you just want to display a buffer, it's fine. But if you want to rotate the buffer with the rotation property, maybe the constraints will be different for the buffer, and that's the case for instance with Intel hardware, I think, maybe other hardware as well. So to be able to give constraint sets, KMS needs the whole KMS configuration for all CRTCs, planes, and everything like this. So in our proposal, KMS takes the whole KMS configuration plus the frame buffer width, height, format modifier. And with all of this information, it outputs a set of constraints that a buffer will need to be allocated with for this usage to be fine. So one possibility will be to make a diam mod addfb handle 0 BO handles as a special case. I think we've talked about this last year, but so calling addfb with 0 BO gives a fake frame buffer that can only be used for test-only commits. And if you use this frame buffer, it gives KMS the information what is the width, height, format modifier. And then KMS could fill out FB constraints PTF blob property with a constraint set. There are a lot of questions. Maybe it would be better for user space to be able to pass a list of potential modifiers to be used. So yeah, we still need to discuss about this.
Yeah, I'm going to jump past GBM. It's really simple. We had a constraint set to the existing call. And this is an example of the merge library. You're going to jump past this too. Sorry, Simon. But look at the link there. That's Simon's code. I want to make sure I got this slide up. Here's a link to our workshop. So obviously there's a lot of questions. Please come and join us for the workshop. We can discuss all the open questions there. I think we're mostly out of time for questions now. But also look at the next slide in here. This is a list of our references. This includes a detailed discussion. The entire email that Simon and I went through to come up with this design is archived there, unedited. So take a look at that as well if you have questions on how we came up with these ideas.
Okay, we are exactly on time, and thank you very much, folks, and we can continue that tomorrow during the workshop, right?
Yep.
Okay, thank you again, and see you.
Good morning. Yeah, well, it's in the afternoon. It's afternoon. Sure. Let me go tell my daughter to be quiet.
Okay, Alex, the stage is yours.
Thanks. All right, I'm Alex Deucher. I work for AMD, and this talk is about why peer-to-peer DMA is so challenging on Linux, and I guess challenging on more than just Linux, but this is focusing on Linux. So to start things off, I guess for those of you that don't know, what is peer-to-peer DMA and how does it work? So peer-to-peer means device to device, and DMA is direct memory access. So you have devices accessing each other's resources directly without going through system memory or through the CPU. Platforms generally have a system physical address space, and then within that they have apertures that are defined for I/O space. And on a lot of, for example, 32-bit platforms, I mean, you have to divide that 32-bit physical address space between I/O and memory access. So you have a pretty limited window, and on modern devices with a lot of memory or large doorbell apertures and things like that, I mean, it takes a lot of memory. So on newer 64-bit platforms, I mean, we have a lot more space. So you'll often have multiple apertures, a legacy one below 32-bit, and then a larger one up at a higher address range, where you can map, either remap or directly map the bars of your devices. On PCI devices, the bars are what we use. I mean, they're ostensibly for CPU access, but you can access them with another device too, as if it were system memory, and you can do a direct peer-to-peer transfer. I also mentioned a couple of vendor-specific interconnects here, XGMI, which is AMD's, and then NVLink. They are often faster or provide different coherency guarantees compared to PCI or PCIe, but they're not generic solutions. So, but you may run into them in the discussions of peer-to-peer. So, why would you want to do peer-to-peer DMA? Like, what is it good for? Well, obviously it saves a trip through system memory if you don't need it, and you can build pipelines without any CPU overhead or synchronization. So, I mean, if you think about it, you can have a pipeline where you kick off an operation on the GPU, it processes some data. Once it's done with that processing, it can, via a peer-to-peer transaction, can hit a doorbell in another device's bar, like say an RDMA controller, and transfer that data to another node in a network. All without any CPU interaction. So, it has a lot of advantages. And now you're probably thinking, well, this sounds great. What's the catch? Well, the catch is PCI never really formally defined peer-to-peer. In the early chipsets, maybe it worked, maybe it didn't. That's improved a lot today, but there's still no standard official way to tell if a particular chipset supports it or not. In the kernel, we have a whitelist of which platforms support it. On the AMD side, all Zen chips support it for both reads and writes. On AMD PCI chipsets prior to that only supported it for writes. Intel has some limitations on some platforms, like I think it doesn't work over QPI links, but it does in some other cases. I'm not sure the overall status of which platforms it works or doesn't work on. And then for non-x86, I have no idea, but it's hit or miss. And then the other thing is there was no IOMU, and it's still largely the case on other OSs. But the important thing there is that the IOMMU can provide I/O remapping, and so if you end up on systems with I/O space up at high addresses, you might have a device that has a pretty limited ability to address physical addresses, and you need some device to be able to access a bar that's way up there at a high address. So those are kind of the reasons that it's been problematic historically. So, I mean, you're probably thinking, well, it sounds like Linux can handle this now. What's the problem? Well, it didn't until recently. So, a lot of other solutions filled the void to begin with, and they tended to be sort of proprietary and, not really upstreamable. It often fell down to, passing around system physical addresses being the lowest common denominator and the most expeditious route to support it. So there's a bunch of existing APIs out there. The GPU direct and peer direct stuff from Mellanox and NVIDIA, and the direct GMA stuff from AMD. These were largely focused around high performance compute and workstation use cases. Where usually those users tended to be tied in into proprietary systems pretty heavily, and had large entrenched user bases. It also didn't help that until recently Windows didn't use the IOMMU, so passing around physical addresses kind of just worked, whereas on Linux the IOMMU has been used for IO remapping for ages. And so if you pass around physical addresses, you're not necessarily passing around real physical addresses, you're actually passing around IO virtual addresses for a particular device. So, a lot of times the advice for workstation users was, if you wanted to use these APIs, you needed to disable the IOMMU, which kind of, prevents all the capabilities that it provides. So now that we do have some solutions upstream, kind of talk about the two of them. There's two of them in tree, and the first one is the peer-to-peer PCI DMA API. It was largely designed around NVMe fabrics offload, and the model obviously is reflected in the API. It's very similar to the DMA API, where you have a the person that wants to use the remote, in this case the client that wants to use the remote resource, would allocate the memory, and then it's sort of pinned as long as it needs it, and then when it's done with it, it's freed back to the subsystem. So you have these sort of three constructs. You have a provider which registers their resource, and then you have a client, which is who allocates the memory. And then there's an API to allocate the memory, and then you would call something like PCI P2P DMA map SG instead of the standard DMA map SG if it's device memory, in order to map it. And then you also have this idea of an orchestrator, which is another possible thing involved that could orchestrate the transaction if you have, say, multiple paths to a target or something like that on a large system. Memory is always pinned. This works well for the specific use case it was added for, but it doesn't for a lot of other use cases. Then we have DMA buff, and this recently went upstream due to a lot of the work from my colleague Christian Koenig. And DMA buff is a framework for sharing buffers and hardware across drivers. It was largely used by the GPU and video for Linux drivers. Recently, it gained support for allowing unpinned access to memory using DMA fences. It also has some synchronization mechanisms as well that the other API did not, that allows for some sort of more advanced pipelines and stuff, but there are some challenges with that. The programming model obviously reflects its use cases similar to the peer-to-peer PCI APIs. You have an exporter which allocates the memory and shares it, and then you have importers which import it and do what they need to do with it. It's not page backed like the peer-to-peer API, so you need to use a different method. So the importer might have to do something like DMA map resource in order to map it into its address space. The exporter registers DMA buff callbacks on it. The importer can register a callback. It's not this slide is not quite correct. It's the move notify callback that the importer can register is not for peer-to-peer per se, although it's a requirement of it, but it's actually for the ability to deal with the resources moving and needing to invalidate and recreate its mapping. And that allows the resources to not have to be pinned. And for things like GPUs, where VRAM is a very scarce resource, it allows more flexibility. And then HMM, this isn't really a peer-to-peer system. I bring it up mostly because a lot of people think HMM is the solution to a lot of problems in the kernel, but it's not exactly a peer-to-peer sharing system. It's a mechanism to provide a shared virtual address space for multiple devices. At the moment, it doesn't have a mechanism for doing peer-to-peer, but I believe there are some discussions about possibly adding that functionality. It might have even had it in an earlier revision. I don't remember offhand. But this is just a little bit of more information about what it does here and how it relates. And then major use cases. So I mean, this is just an example, but I mean, there's obviously a lot more you could come up with. But I mean, very common ones are using GPUs plus RDMA NICs or possibly NVMe devices, and to build pipelines of computation and transfers, or being able to stream data directly out of storage directly into a device for where it could be used. Unfortunately, these different subsystems use different P2P frameworks, and so I guess the question I'm posing here is, is there a way we can make this all work together? Historically, RDMA controllers assume that memory will be pinned, and their whole sort of programming model kind of depends on that. With GPUs, VRAM has traditionally been a very scarce resource, or if not necessarily VRAM, then the bar. Often on older systems with only a MMIO aperture, below 32 bits, you have very limited bar space, so you might only have 256 or 128 megabits of accessible device memory. That's less of a case with bar resizing and 64-bit platforms that have large bars support. So can we make it work? We traditionally don't want to pin VRAM, but on systems with a lot of GPUs, you may end up actually having more VRAM than system memory. And so is it really the scarce resource that it is, has traditionally been? And sort of just food for thought, stuff we can kind of think about here is maybe we can pin VRAM in order to support pipelines involving RDMA NICs or NVMe, for example. And maybe RDMA controllers with on-demand paging support could support VMA buff, and being able to deal with the fact that memory might end up not being pinned all the time. And that's it. Questions?
So far, I do not have anything. So,
all right.
Wait a second. Well, then I guess that's it. Thanks a lot for the talk. And then we're going to have the lightning talks and a demo. But it's going to be in 15 minutes. Thank you.
Hello. So welcome to my Lightning talk. First off, I would like to thank Codeweavers for making it possible for me to be here and host this lovely event for you. So I'm Arek, and I'm one of the IGT maintainers, and this is my annual IGT update. So first off, i9-15 perf was pinned into a library that installs along with IGT. So if you want to use anything for i9-15 performance metering, you can use that library. IGT Core also has a new thing called IGT Abort. So maybe a little bit of a background of what IGT is. It's a set of tests and tools to aid DRM driver development. So IGT Abort is a way for you to abort the execution of the whole test run from inside of a test when you detect an abnormal condition. So normally we abort execution on wedges or other taints that are serious enough, and this allows you to detect those conditions from the test. And if you find something that okay, the test probably shouldn't run past that point because machine is some weird state, you can use it. There are a couple of notable test additions, like we have KMS write-back tests in IGT right now, and also recently there was sync object timeline tests added. In the last year, we worked on Chameleon reliability quite a bit. And sorry, Martin threw me off. So Chameleon reliability work. Chameleon is a display emulator made by Google, and it has serves as a display, and we can fake EDIDs, read the pixels of it. The issue is with other tests. So if you're using that Chameleon as a normal display, and if it's not in a known working state, you can have other tests flip-flopping. Like if your test requires 2-3 screens and Chameleon is the second screen, then if it's not up, then your test results will be thrown off. So we added a lot of things to make sure that Chameleon is actually up at the beginning of each test that touches display, and to make sure that it's in a working condition. If not, then we use the before mentioned IGT abort to abort the whole execution, saying hey, Chameleon is faulty, please take a look at it. There was a lot of coordinated effort to optimize the test suite execution time. So we started tracking how long it does take to execute certain tests, and if something was running over that threshold, we tried hard to clamp it down, either by limiting the number of iterations or just instead of using iterations, using the time criteria. Also, we switched the kernel self-test harness, so you can use IGT to run DRM in i9-15 self-tests. To get those test results in piglet format, and now it uses the new infrastructure inside of IGT, which is called dynamic subtests. So this is something for enumerating the tests on the runtime, because classical tests have to be machine independent, so you can enumerate them on any machine, and they have to just worst case scenario skip. And kernel self-tests are kernel dependent, so depending on which kernel you have deployed, you may have certain tests or not. So having to change that each time in IGT would be a little bit cumbersome. Also, we now have multi-GPU hour tests, and dash device selector can select multiple GPUs. And we have sample test that uses that new API, which is KMS prime. So you can select which two devices you want to test prime between. Other than that, we have better asserts for invalid nesting of magic control blocks. So IGT depends on magic control blocks like IGT subtest, IGT skip, IGT assert, and there are a couple of ways that are there are multiple ways which you can nest one inside of the other, but there are also plenty of invalid nesting scenarios. And we now loudly assert on those and print a message explaining what went wrong. We also have better kernel module param handling, so some of the tests want to override some of the kernel parameters, and we have now a generic framework in place that allows you to store the original kernel settings, mangle them a little bit, do some testing, and restore the original state. We have also threading in tests, so asserts from threads launched from inside of a test were causing a lot of very weird failures, basically the thread was jumping into something it shouldn't jump, and there were confusing errors all over the place. Now it's safe to use asserts inside of threads, and IGT skip and require are not allowed, and we just assert on them using the standard assert to exit execution early and complain to the user. Another things, couple of improvements in IGT Runner. So we have a per test timeout. So this was used in the execution time optimization effort to hunt the tests that are taking too long. We have more reliable output. There are a bunch of sync points added and making sure that we actually write the results back to the disk. And we introduced a switch to enable disk usage limit. That's quite a lot for a year, and thanks for hanging by, and that's it for my talk. Thanks.
Hi, hello everyone. I'm Pierre-Loup Griffais. I work for Valve on most things Linux, and today I'll talk a little bit about Gamescope and update on its development and show a couple of quick demos. A little bit about myself. In 2007, I started being involved with the Linux graphics stack, mostly on graphics drivers at the time. In 2012, I joined Valve to work on the initial Linux port of the source engine and the Steam client. Did lots of OpenGL performance work, worked on kicking off SteamOS, and then later things like Vulkan, SteamVR for Linux. In the past couple of years, I've worked a lot on setting up all of our external open source project contributions. Some of it you might have seen today around the Mesa project, and maybe in the coming days at the event as well. So a quick update on Gamescope. So what is Gamescope? Gamescope is essentially the continuation of Steam Comp Manager. It's a refactor of Steam Comp Manager to be based on Wayland instead of GLX. So Steam Comp Manager was or still is, the GLX-based compositing window manager at the core of the SteamOS gaming shell. So it either presents Steam or a single game in a full-screen way, nicely scaled up with pillar boxing or letter boxing if needed, V-synced, all that kind of, or what we call the appliance-like session. So by moving over to Wayland and X-Wayland, we're able to basically do the same thing and display a single game running in that X-Wayland instance, but we more directly assume the role of what would be the responsibility of the DDX back then, and we get to then decide what we do with the incoming app buffers, and either short circuit any sort of graphics and go directly to DRM display output, or if we need to composite something, the new code uses Vulkan only. So that by using Vulkan Compute, we're actually able to schedule any work needed on the async compute ring of the hardware if the hardware does support that, which is pretty useful in some situations. It's also optimized for latency, so it tries to be very aware of the underlying VBlank timing of the output display device when it's running in that direct DRM embedded mode, and tries to align the game's rendering to that and decide which of the most recent buffers composite or display at a tight deadline before the next VBlank. So that's the basic kind of rendering loop here. You see VBlanks are the vertical purple bars. This is running on AMD hardware, so we're able to use that real-time compute capability in that separate hardware ring. Here you see the game running. Sekiro is very intensive for the system apparently because it's keeping the GPU completely busy. But despite that, we're able to get scheduled at our budget before VBlank, sneak in some compute work even though the GPU is completely busy, and still make our frame there. So for the whole Wayland aspect of it, I use WL roots. Seemed to be a pretty quick starting point and to fit our needs as far as not having too high level of an abstraction, because I knew that there's some parts of it we would need to completely stub out and replace with our own, such as the whole output portion with graphics and the window manager as well, where we substitute WL roots with our own window manager, still based on the previous Steam Comp Manager code base. So once I managed to hack around these mismatches, it was pretty painless. I started from Rootston, which was, I guess, an example compositor based on WL roots. Had a nice disclaimer at the top saying, under no circumstances you should fork this and create your own compositor from it. So I did that, and then once that was up and running, merged it with the Steam Comp Manager code base, and then started to plumb the output pipeline of Steam Comp Manager to Wayland by putting my own sideband to export the DMA buffs from Wayland. And once that was running, I just had to remove the rootstown part of it to get back to a normal size and bare bones functionality. So in that intermediate state, it looked a little bit like that, where it had both the rootstown window showing a more traditional desktop and or more like managed, scaled, nicely presented output window, which was pretty interesting. So as part of developing it, I was mostly using a desktop session because Wayland and its compositors usually have some sort of nested support where you can just run them on a normal desktop. And was mostly using that as a development tool because it was convenient. But I was running through that stuff, realized that the same architecture, the same code base could actually let us achieve some of our goals around doing the same sort of input-output manipulation of the pre-existing game without modifying the game, but applying that to a more general Linux desktop, which was really interesting. So it seemed like we could hit two walls with one stone here, which I tried to pursue some more and added some initial features to see what we could get out of that nested desktop use case instead of just focusing only on the embedded one. And I'm going to show some of my takeaways there. The initial thing that it obviously does is to abstract away all the size of the output. So if you have a game, you're able to put it full screen, and and that's pretty straightforward. It's nothing that Steam Comp Manager couldn't do. But say you have an ultra wide screen. Here, I put my monitor in its native 21:9 mode. Some old games will probably not do the right thing when faced with these kind of modes. Newer ones support them just fine in most cases, or at least have a fallback to 16:9 with pillar box. But some older games will just never be made to work well there. So here, is Portal. You get to pick your poison in there, but no matter what you pick, it's not going to work quite the way you'd expect and not give you, both full screen and not broken rendering. But if you run it through Gamescope, which is a very easy command line, just append or prepend Gamescope with 2560 height 1440 to make its internal display a 16:9 and pointing the game at that, so it runs in that little sandbox. Then as far as the game's concerned, it's running on a single 16:9 display, and then all of the output transformation around putting these pillar boxes around the rendering and overlaying the rest is done through Gamescope. So it works more as you'd expect there, and latency is good and all that. Similar situation on multi-screen scenarios like multi-monitor. Some games will either get endlessly confused by multi-monitor configurations and just pick one display and be insistent that they need full screen to that one, and then not react well when you forcefully uproot them and put them to the other display. Or some games, if you have like a portrait display and a landscape display, some games will get very confused by the overall desktop resolution and all that. If you run it through Gamescope, as far as the game's concerned, it has one display. It has no way of hurting itself there. So you can just unfull screen it through Gamescope, drag it to your other display, and there you go. It solves that whole class of issue as well. It can do some interesting things around refresh rate as well. So by default, I can run this GLX Gears OpenGL benchmark, and it'll naturally pass through my host desktop refresh rate of here 100 Hertz to the app. So it's running at 100 Hertz right now. But should I decide to, I can just tell it to fake it and run it at a refresh rate of 30 Hertz, which can be useful in some cases if you need to cap an application. And some ad hoc tools have existed to do that for a long time, where you can just hook to a variety of graphics APIs and try to get the same thing going. But here it's a nice general solution and work across the board. And then you can imagine more quality of life type features where here I have this mode where it limits the refresh rate, but only if the Gamescope window is out of focus. So here it's running at my native 100 when I'm trying to interact with the app, and then as soon as I alt tab, it's throttling down to 10 FPS. So say you're gaming on a laptop and you want to have your laptop get a little bit cooler if you need to alt tab from the game, or not be burning all that battery life. Maybe you can do that now. The fact that it has this unified Vulkan-based output pipeline in the nested scenario is pretty interesting too. It means that you can, for example, use the VK Basalt post-processing Vulkan layer on a variety of applications that it would otherwise not support. So, for example, here I can run it with GLX gears and make use of its CRT filter that would only apply to Vulkan apps normally. And in conjunction with Gamescope's own feature of disabling filtering and doing that nearest neighbor filtering, you can get this nice retro output going there. Same idea, you can just extend that to core rendering as well, because everything goes through that same output pipeline. So it's general solutions to things that were previously hacked together, and I think it could be pretty convenient if exposed properly with a nice UI. So, I mean, there's still some work to do. Definitely more polish around that nested experience. Like, that's just starting at this point. Mimic more the game window, pass through the window title, window icon, a couple of different things that, would just make it act more as you'd expect as the user. Of course, we need NVIDIA support as well. Like, it works on Mesa drivers right now, but all of the NVIDIA stuff is off limits because of its reliance to X11 right now. On the embedded kind of core use case, we really need to be able to make more use of DRM planes when possible. And right now it's mostly not possible because of kernel bugs, but it's one of the main things that still forces us to composite when we have additional layers, on top of the game's rendering. There's a couple of, I think, high-level takeaways. We really need modifiers. Like right now, we're focusing on the Vulkan case because we're running the same Vulkan driver on the compositor side and the client app side in the most common case you care about. So we can we can get optimal rendering or optimal surface layout there and just have it match by chance. But for OpenGL, for example, we have to disable all the internal driver compression optimizations and all that, because otherwise our rendering would be garbled, and having modifiers plumbed everywhere is really needed there. Implicit sync's not ideal. It'd be better, I think, if we got an explicit fence if we wanted it, that we could even wait on the GPU. That would be best. There's a bunch of bugs in display drivers on the kernel side. I don't think that's news to anyone. Anytime you're going off the well-trodden path of just doing a native resolution, main plane scan out, you run into issues. And so I'm sure we'll run into more of them, and hopefully that'll be a forcing function to get some of that stuff fixed. It'd be really nice to get tighter control over the application's rendering cadence so that we could, do further things to align its frame, the application frames to VBlank and reduce latency even further. There's some hacks we can do right now, but it'd be nice to have a real mechanism to dictate when things like swap buffers or acquire next image returns, so we could meter it really accurately. And yeah, that's mostly it. I didn't have tons of time, so I tried to go through it quickly, but let me know if you have more questions, and check out the project. It should work pretty well on desktop today, at least on AMD hardware. Intel's probably not too far off from working as well. Thank you.
Okay. So Dorota, I think you're live, and you can take it from there. Apparently the sharing is not working nicely. Maybe we can exchange. James, would you be ready for your talk?
Yes, in theory. 1 second here. Okay. I'm going to present briefly on the Vulkan presentation timing extension that we've recently made public on GitHub. So some history here. The extension that we're working on now evolved from the Google display timing extension that's already public. It has the same fundamental features. I'm not going to try to go into the motivations behind why we're doing this or what exactly it has, but just briefly, it allows applications to provide a target presentation time whenever they present a buffer. So when you call VKQ present, you can say, I want it to happen actually at this absolute time or this relative time. That's also under debate. And you can also query when past presents completed or when they actually landed on the screen. Ideally meaning when the pixels were actually visible to the user, whatever that means for your target display. Oh, did it go away? Let me share my whole screen. Not working? Okay. Okay, so yeah, I was going over the first line there. So we wanted to standardize this functionality in Kronos. So we started an effort to develop a Kronos ratified extension based on the basic functionality from display timing. We added various bits of functionality along the way. We added support for variable refresh rate displays and how to report them, how to operate on them differently. We added additional time domains. So for example, the Google display timing extension, I believe only supports clock monotonic raw as a time domain. To support Windows, we added the query performance counter time domain. And we also added a swap chain local time domain that was required to be the by default. And that would be a timestamp value that is only relevant within that swap chain. So this is useful if you have displays that are potentially in fact remote displays, or if you have a clock for your display engine that's only available on your GPU and it's hard to convert it to other time domains on the system. We added negotiation, a rather complex mechanism to negotiate raising or lowering frame rates where the driver can be given hints that the application wants to boost up clocks to jump up to a higher frame rate after potentially falling back to a lower frame rate in the past. And then that driver in turn will hint back to the application when the GPU is ready to handle that. So we did a lot of work here. It took a lot of time to develop these features. They're relatively complex. But at some point we ran into some problems, namely that we had only intermittent attention from IHVs and ISVs. This all started off with some good attention from various people giving input and doing development and getting feedback on hardware. But at some point, interest would kind of wane, or different groups would have different priorities going in different directions. So we really struggled to get the level of feedback necessary to validate our methodologies, which were honestly much more researchy in nature than other stuff we've usually done in Kronos. At the same time, right around when this was kind of losing interest internally, some of us noticed that at XDC 2019 last year, there were a lot of talks on things that were related to presentation timing. People doing custom VR compositors or their own custom system compositors even that needed very accurate display timing to behave well. So a few of us thought that it might be beneficial to make this public, both to spur development and interest, and to be able to get more validation and more input from a broader group of people. So we went through a very long process in Kronos actually to convert this into an EXT extension, remove any NDA components of it, and make it all public. And as of Monday, it's public on GitHub now. I can't change slides. So now that it's up there, patches are welcome. Please contribute. Please read the spec. Please do whatever you can with anything public like that. Send pull requests, point out typos or anything trivial, or make high-level suggestions. We do have some specific requirements regarding contributions to keep the option open to make this a Kronos ratified extension later on. But for right now, the goal is just to make an EXT multi-vendor extension that wouldn't have any special Kronos protections. So see the pull request that has some details on how to contribute in the description there. Some ideas for contributions include, implementing your favorite driver, Windows system, or whatever. If it's difficult or not possible to do that for some reason, definitely let us know. We're trying to make it compatible as widely as possible. Also, write support for it in your app, toolkit, game, media player, VR compositor, or whatever, anything that uses different presentation. Again, if that's difficult or not possible, let us know why. One caveat here is if you're going to write support for this in drivers or applications, it would be best if you somehow hid it from being enabled by default, because the API is not final. This is an under development specification, not an extension release. So the API will probably change, and it would break apps once we change that, or break old drivers in the future. So just leave it off by default. But other than that, go wild. If there's any questions, let me know.
Yeah, let's keep the questions for a bit later, maybe at the end of all the lightning talks. And yeah, so that's it. Oh, Dorota, do you mind trying again?
Of course.
Aha! Ta-da!
Okay, thank you, Martin, for introducing me. I am Dorota. I've been specializing in Wayland recently, and I've been trying to push input method support in Wayland for a while, and this is just the newest update. A quick recap: what is an input method? It's when you enter text, when a human controls a tool to communicate to some software in order to produce text and send it to an application. This is an input method. Traditionally, it has been a separate subsystem from the keyboards and used mostly for languages from the Chinese family, like two versions of Chinese and the Japanese kana, but it's not just that. So in Wayland, we have 3 protocols for that. One is text input, which is the base, and the other 2 are input method and virtual keyboard, which allow third-party applications to connect to that system. Those are the 3 ones that I try to get right, but things don't always go right, so I'm just going to tell you about the failures that I had. The first problem was about key maps and with virtual keyboard. When we have a virtual keyboard and a real keyboard, and both of them have different key maps, we might want to press a modifier on one and a key on another. But which key map decides the outcome? This is a problem without a clear solution at this moment. There's another problem with virtual keyboard. Input events which come from libinput, which are related to real devices, carry timestamps, and timestamps are used to ensure the correct ordering of events. But the clock is not very clearly specified in Wayland, so it's not sure how the virtual devices would send their own timestamps. A solution is in progress. Another problem is related to text input, the core protocol, and it's about deletion. If we want to delete a character, the application tells us what's already written in the text field, so we can count bytes and delete as many as needed. Great. No, not so great. The application is not forced to tell what the text field contains, because I made this optional in the protocol. So we don't always know how many bytes to delete, and we can not actually delete things properly. And this is getting fixed in the next revision. So those are the most important problems right now, but there are more problems that I have already been told about, and there are more problems that are certainly going to pop up in the future. So if you're interested in that kind of stuff, you should join the discussion on the Wayland protocols mailing list and on the GitLab instance and try to help with that. And you can also try reading my blog or talking to me on IRC, because I blog about those topics sometimes. Yeah, thanks. That would be it.
Thank you, Dorota. And finally, we have Alyssa.
Hello. Can you hear me?
Yes, we can hear you, but
magic.
Dorota is still sharing. Or is she?
I'm not, sorry.
Okay. Oh, okay. Well, that worked.
Right. Hello, everyone. I'm here with more witchcraft noises. Ooh! I wasn't really rehearsing my witchcraft noises. I'm sorry. This was supposed to be a lot more suave. Anyway, the product of reverse engineering is very ad hoc. You have a number of bits and pieces understood, along with other bits and pieces that aren't so understood. And sometimes you have very clear code, such as the type that you'd see with drivers that are based on official documentation. And other times you have code that has to do an XXX 3 times in the same comment because you're just moving some magic field, some magic number into some other magic field. And I mean, it works. I'm presenting from my Pantfrost laptop, but it's not ideal, and it's not the sort of sustainable code quality that we would like to see. So the question is, what do you do when all of a sudden you want to transition your driver from based on ad hoc reverse engineering to potentially being based on much more solid foundations? How do you all of a sudden refactor your entire driver to have all of the hardware-specific code renamed and fixed? And in addition, if you have debug tooling, such as disassemblers or command stream decoding tools, suddenly having those all rewritten and re-engineered to be based on new foundations. This is a problem which perhaps Pantfrost has faced or is facing. And one of the solutions for us has turned out to be moving to more auto-generated tooling. On the data structure side, the command stream side, it is very helpful to focus on moving away from just ad hoc bit fields to using tools like GenXML or NVTools, which a number of drivers are already doing. If you look at the difference between manually packing fields into a pack struct versus these very nice generator functions you'll see in the Intel or V3D drivers, that's something that we would ideally like to replicate. So in our case, we switched to GenXML for the data structure side, and that is in progress. On the compiler side, it's not as clear-cut how to handle this because compiler development, the instruction sets can often be much more irregular than you would see on the data structures. And so GenXML, for instance, would not work for the Bifrost instruction set, which we have been focusing on for this refactor. To this end, we can still use a XML generator-based solution. And from a given XML description of the instruction set, we can generate a disassembler for the instruction set, which handles every instruction with every modifier, as well as helpers to efficiently pack all the instructions at the last stage of the compiler. So this work is well underway for Bifrost, and indeed, the code has now landed in Mesa, or is landing as in the past few minutes. And if I share my screen, which I'll have to remember how to do on Jitsi. Not used to this whole online conference thing yet, but we'll get there. We have this merge request to rewrite our disassembler and the instruction packing to be canonical. And here's Lightning Talk. And if we look at the actual source code for here, we have a very streamlined descriptive version of the instruction set going through all different instructions methodically sorted with our exact fields, which are a generalization of opcodes, as well as all the different modifiers that you might have. And altogether, a series of Python scripts that can run in the build system, just like we do for GenXML, is able to generate everything we need. And so the net result is that we are well on our way to having turning Panfrost into a stable, very clean code base, which will be ready for serious Bifrost work going forward. I'm assuming there are questions in the chat, so I'm happy to. My screen is being shared.
Yes, perfect.
What is meant by
shit, what was the password again?
You said it.
Talks done quick.
Are you streaming again? Have you started the stream?
Not yet.
You've got an unused variable in release,
See,
which I guess is only
OBS.
for
Apparently this is there.
Welcome back, Martin.
Am I going to be coding on the live stream? Is that how this works?
He's
how
back.
much of a work? Are we streaming again, or?
No. Oh, are we? We are.
We are.
Live,
Awesome.
Yes, okay. So just for your information, one of the switches that I put today apparently is just shitty. And after 8 hours, it just decided to give up. And I thought it was a good idea not to go through the router. Oh well. Okay, so sorry about this. Please continue.
All right, so everyone in chat can hear me then? Somebody say something in the Q&A channel. Guess there's lag to YouTube. Yes, awesome. So to answer Jason's question, in what sense is this canonical? This is canonical in the sense that this is the syntax and instruction names used by ARM internally for the upstream LE stack. And this work on Bifrost is being done in partnership with ARM as in technically supporting us. And we are looking forward to seeing Panfrost mature in the years to come as a more official driver. So it's pretty phenomenal to see. It was only 2 years ago at XDC that Liud and I kicked off Panfrost as a reverse engineer driver. And here we are moving a bit to be anything but. So there you have it. That's how it's canonical. And not just because it runs on Ubuntu, but you know, there are ARM being built out there. So if that's it, I guess I'll do my witchcraft thing and break the other switch. I mean, ensure that the stream can keep going for the last lightning talk of the day, and so there's not any issues, and then do my witchcraft thing. So,
but I think you are the last one.
Oh, then I can't break the stream.
Well, you did.
Yeah, well, there was an issue with the spell, and I'm just going to stop talking now because Fifth Amendment rights or local jurisdiction equivalence.
And Daniel, did you want to say something, or you did already?
Yeah, no, it's all covered.
Okay, very good. So that's a wrap for the day. It's good to finish on a high note of adrenaline, and so we'll see you tomorrow and for another day. Hopefully a bit more stable, and I think tomorrow morning I need to go buy another Switch. Very good. Have a good evening or afternoon or morning, and take care. Bye-bye.
Cool, thanks.